You lie beneath a sky that looks calm, patient, familiar, and yet our address is anything but ordinary. The Milky Way, with all its quiet suburbs of stars, appears to sit inside a vast hollow in the cosmic web, a region so underfilled with matter that space itself seems to loosen there, as if the fabric were breathing a little deeper. In 2013, 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, assembled lines of evidence that pointed to this unsettling possibility. Count the galaxies, they said. Calibrate their distances with supernovae that explode at predictable brightness. Compare the nearby universe to the universe a bit farther out. The numbers kept repeating the same whisper locally: there are fewer galaxies than average. The result became known by their initials, the KBC void, and it quietly placed a hand on the oldest assumption in cosmology and pushed. So before we continue, hit like and subscribe so you don't miss a single revelation as this story unfolds, moment by moment in real time. Tell me in the comments where you're watching from, what time it is there, and whether you believe we're hearing the whole truth about what's unfolding above our heads. And if you want to keep the signal alive, share this video on X, Facebook, Reddit, or even just with the people who still look up at night. You are the reason we can keep following the impossible, and for that, thank you. The cosmological principle is the assumption that on large enough scales, the universe is homogeneous and isotropic, the same in every direction, the same at every place. It's a promise that lets us use one set of equations everywhere, from the edges of the observable universe down to the room where you're listening now. But if our neighborhood is a deep underdensity, roughly 20% below the cosmic mean over a region approaching 2 billion light-years across, then measurements made from here will carry a local accent. We would still be speaking the language of the universe, but with a bias you can't hear until you notice it. Keenan, Barger, and Cowie approached the problem from multiple angles. They used galaxy counts from wide surveys like TOMAS and the Sloan Digital Sky Survey to see how the number of luminous systems changes with distance. They folded in type Boyer supernovae, whose peak brightness serves as a cosmic standard candle, to trace how fast space expands nearby versus farther away. Layer by layer, the picture sharpened, the nearer universe looked suspiciously sparse, and the density increased as the team looked outward, as if we lived in the soft center of a gigantic cosmic bubble, outlined by brighter, busier walls. If that sounds like we've put ourselves back in the middle of everything, like some modern echo of an ancient geocentric mistake, pause and breathe. The claim is not that we sit at a privileged bullseye, only that our region is underdense. In a vast, sponge-like cosmos made of filaments and gaps, someone is bound to live in a gap. Statistically rare does not mean impossible. It means surprising, and science is made for surprises. What would an underdensity do? Gravity is weaker when there's less matter. In a weaker gravitational field, there's less resistance to expansion, so space inside a void can stretch a little faster. Light that travels through such a region also behaves subtly differently. As photons cross a low-density zone, they encounter shallower gravitational wells and can emerge with slightly altered energies. This is one reason cosmologists study the integrated Sachs-Wolf effect, tiny temperature shifts imprinted on the cosmic microwave background when ancient photons traverse evolving structures like voids and superclusters. A great hollow can leave a faint cold fingerprint on the oldest light in the sky. Stand with that for a moment, a hush in the nearby galaxy count. A faint cooling in the afterglow of the Big Bang, a nudge in distances measured by supernovae. Each thread is delicate. Together they weave a story that our local patch may be less average than textbooks once promised. To picture it, imagine the universe as a dark ocean of glass threaded by bright, delicate filaments. Along those threads sit the clusters Coma, Perseus, Pisces, Shapley, great knots of galaxies where matter pooled and cooled. Between these walls lie the hollows, the quiet basins in which very little collects. Our Milky Way seems to occupy one of these basins, not empty but thin, not void of structure but gentle in its gravity. The boundary where the density climbs back toward the cosmic mean appears a few 100 million parsecs away. Beyond that, the web resumes its intricate rhythm, brighter walls, thicker strands, more typical statistics. KBC's analysis gave this hollow a number, a mean density contrast, DRR, of about 0.2. In plain terms, 20% less matter than average across astonishing distances. In most areas of physics, a 1% change would be enough to fuss over. Here, 20% is not just a wrinkle, it is a weather system. It means light time and distance inside the hollow are all shaded by where we live. This is why the finding stirs more than curiosity. Our most quoted number for the expansion of the universe, the Hubble constant, depends on local measurements of distance and recession speed. If space inside a void stretches more freely, then measurements made within it tend to record a higher expansion rate than those inferred from the early universe's relic light. You can feel the tension, even without the equations. Two careful yardsticks, two excellent laboratories, two values that simply refuse to meet. This Hubble tension might be a symptom of new physics, or it might be a signature of old physics viewed from an uncommon neighborhood. KBC does not claim to end the debate, it clarifies what's at stake. The elegance of the original work is its restraint. It does not lean on one kind of data. Galaxy counts alone can be tangled by selection effects. Supernova distances alone can be biased by calibration. Large-scale structure alone can be ambiguous when mapped from a single vantage point. But when these threads reinforce one another, and when independent surveys echo the trend, the whisper becomes a tone you can no longer ignore. Our corner may truly be hollowed. Gentle gravity, easier expansion, quieter clustering. Even the poetry of the cosmos seems to agree. Simulations of structure formation show voids as natural, inevitable features of an evolving universe. As filaments feed their clusters, the spaces between them swell and smooth. Over billions of years, the hollows inflate faster than the walls thicken. Voids merge like bubbles in rising dough. None of this requires magic, only time gravity, and a little dark energy humming everywhere at once. But the particular scale of this hollow, the calm breadth that KBC outlined, is large enough to make cosmologists tilt their heads. It's not unprecedented, only improbable. And improbability is exactly where discovery loves to live. If you're listening in the dark, let the thoughts settle. We're not lost in emptiness. We're held by it. The underdensity around us is not a flaw in the universe, but part of its architecture, a quiet atrium and a cathedral of threads. It changes nothing about the stars that rise and set, yet it might change how we count them, how we time their distances, how we tell the story of the whole. The discovery did not shout. It was published, checked, debated, extended. It seeped into conference slides and mission plans. Telescopes were tasked to map the hollows more precisely, to lens their edges to watch how galaxies drift at their boundaries. The question the KBC Void asks is simple and enormous. If your laboratory is inside a hollow, how do you measure the entire cathedral fairly? Tonight we begin there in the middle of a gentle absence. We will walk its floorboards, trace its walls, and listen to the way sound carries inside an almost empty room. We'll measure light across it, feel how time moves just a touch more freely, and ask what that freedom does to our numbers. The universe did not promise us a typical seat. It offered us this one, and from here the story of everything might bend in the slightest, most important way. In the next part, we will place the cosmological principle on the table and test its seams. If uniformity is the law, what does our hollow do to it? And how far does the law still hold? There is a sentence that quietly holds the entire universe together. On large enough scales, the cosmos looks the same everywhere and in every direction. This is the cosmological principle, the assumption that turned Einstein's equations from a local theory of gravity into a map for the entire sky. It was not proven. It was chosen an act of faith in the logic of symmetry. Without it, there is no clean geometry, no predictable law that works both in a laboratory on Earth and in a galaxy 10 billion light-years away. It says no place is special, the universe is fair. Einstein adopted that fairness in 1917 when he first dared to apply his general theory of relativity to the whole cosmos. The mathematics of curvature and mass demanded an orderly background, otherwise the universe would collapse under its own uneven gravity or tear apart into chaos. So he assumed balance, a smooth distribution of matter and energy everywhere. It allowed him to draw a simple, beautiful model of a static, eternal universe. Later, when observations showed that space is expanding, his assumption of uniformity survived. The cosmos might grow or shrink, but it would do so evenly like a rising loaf of bread. A decade later, Edwin Hubble, quiet observer on Mount Wilson, confirmed that distant galaxies were receding from us in proportion to their distance. Every observer he proposed would see the same thing. The universe was not only uniform in space, but in its motion a perfect democratic expansion. Hubble's redshift law became the first great proof that Einstein's tidy assumption worked. From it flowed all of modern cosmology, the Big Bang cosmic microwave background dark energy, even the idea of the observable universe itself. Remove the cosmological principle, and every equation of large-scale physics begins to wobble. But the sky has a way of testing the stories we write about it. When Keenan, Barger and Cowie announced evidence that the Milky Way sits in a region 20% less dense than the cosmic average, that symmetry shuddered. If true, the local universe is not homogeneous. It's not isotropic. It is by definition biased. A bias of place, a curvature of context. Cosmologists had long known that small irregularities exist. Galaxies cluster into filaments, clusters not into superclusters. Between them yawn great voids, hundreds of millions of light-years wide. Yet the principle promised that these ups and downs would cancel out when averaged across enough distance. Beyond 300 million light-years, the universe would smooth. The KBC void, stretching perhaps 2 billion light-years, breaks that expectation sevenfold. It's not supposed to happen. If the fabric isn't smooth, then light does not travel through a consistent geometry. A photon leaving a distant galaxy may cross dense walls, empty hollows, and gravitational gradients that stretch and compress its wavelength unevenly. Distances inferred from its color shift our cosmic yardstick, begin to tilt. Even time itself, measured through gravitational potentials, ticks at slightly different rates in different densities. All the clocks in the universe are still synchronized, only because we pretend the landscape between them is flat. Einstein would have frowned at the word pretend. He believed symmetry was not convenience but necessity. In 1917, he wrote that without uniformity, the equations of general relativity could not close. In his vision, space-time was a continuous sheet whose curvature depended on energy and matter, but averaged over large regions it had to even out. Otherwise, every patch of cosmos would require its own personal geometry, a mathematical nightmare. The principle was less about arrogance than about survival. Physics needs something steady to stand on. Homogeneity gave cosmologists a clean background against which the small irregularities of galaxies could be treated as ripples, not redesigns. For a century that faith worked beautifully. Observations from Kobe double map and Planck revealed a cosmic microwave background, astonishingly smooth variations of only 1 part in 100,000. Those tiny ripples seeded everything that would later form stars and planets. To the naked eye of mathematics, the universe looked remarkably obedient to Einstein's assumption. And then the measurements began to sharpen. Large-scale surveys like Sloan and 2MASS drew maps so vast that patterns emerged, walls hundreds of millions of light-years thick, voids larger still, regions where galaxies ran sparse for reasons yet unknown. Each new layer of precision nudged at the same question: how large is large enough for homogeneity? At what point does the principle stop being true? The KBC void reopens that wound. If our neighborhood truly is underdense on scales where the universe was supposed to average out, then the cosmological principle might not be a law at all, just a useful approximation. And approximations, when carried into the heart of equations, can distort everything they touch. Consider what that means for the Hubble. Constant the rate of expansion we use to estimate the universe's age. If we live in a region where gravity is weaker and space expands faster, our local measurements naturally overshoot the cosmic average. From another denser vantage point, the same universe might seem older, slower, quieter. In effect, every observer measures a slightly different cosmos. The constant becomes contextual. It's not the universe lying to us, it's us measuring from the wrong side of the hill. This realization unsettles not just the numbers, but the philosophy of modern science. The principle of mediocrity, that we occupy no special place, has been a moral anchor since Copernicus. It reminds us of humility. Earth is not the center. Humanity is not exceptional, the cosmos is impartial. But if our section of the universe is measurably different, if we're embedded in a gigantic bubble of low gravity, then we are not typical observers. We are statistically rare, not exalted but unusual, and that changes how every cosmological inference must be drawn. Physicist Joseph Silk once said, "The cosmological principle is not sacred because Einstein wrote it. It's sacred because everything else depends on it." And yet science has no true saints. Its creeds stand only until evidence erodes them. When surveys reveal the hollows growing, when void catalogues thicken, and the discrepancies persist, the principle's once immovable symmetry begins to look like a line drawn in sand. Some cosmologists defend it fiercely, others whisper that it was always an approximation. Between those camps lies the most profound humility of all. Maybe the universe is not uniform but patchy, not symmetrical but self-similar, fractal in its balance between chaos and order. Look again at the sky. The Milky Way's bright river curves across it, a thin thread in a web that extends beyond imagination. Each knot of galaxies sits at the intersection of gravity's flow lines. Between them lie oceans of quiet. The pattern repeats on every scale we can measure. Perhaps this too is a kind of uniformity order, not by sameness but by rhythm. Still, the KBC void is an experiment the universe has run for us. If the equations bend here, if expansion really speeds up where matter thins, we will see it in the way light drifts and galaxies move. Future missions, Euclid Vera Rubin, the Roman Space Telescope, are already designed to measure those drifts with exquisite care. They will tell us whether Einstein's old principle still holds, or whether it finally gives way to something richer, less tidy, more alive. Because perhaps the universe never promised to be uniform. Perhaps it only promised to be understandable piece by piece, hollow by hollow. And our task is not to defend symmetry, but to listen when it breaks. Next, we descend into the evidence itself, how astronomers learned to measure emptiness, and what those measurements reveal about the hollow that surrounds us. Imagine trying to prove that you live inside a hole too vast to ever leave. You can't step outside and look back. The only evidence must come from the light that reaches you, ancient photons carrying hints of what they pass through. That is the challenge astronomers faced when the idea of a local void first arose. To detect emptiness, you have to measure what isn't there. They began by counting galaxies. It sounds simple, almost childlike, until you realize that the numbers stretch across billions of light years, and that every count depends on knowing not only where a galaxy sits, but how bright it truly is. The Milky Way itself hides much of the sky behind its veil of dust, so surveys had to sweep beyond it using infrared light that pierces the murk. One of the first great attempts was 2MASS, the 2-micron all-sky survey, completed at the dawn of the 2000s. Operating in near-infrared wavelengths invisible to the eye, it catalogued hundreds of millions of galaxies, measuring how their light shifted with distance. Because infrared light passes easily through interstellar dust, 2MASS could see the universe in full, even through the so-called zone of avoidance where optical telescopes struggle. When researchers mapped those galaxies in 3 dimensions, a pattern appeared. The local region around the Milky Way contained noticeably fewer luminous galaxies than expected. The emptiness wasn't an artifact, it had structure, scale, and continuity. Then came the Sloan Digital Sky Survey SDSS, which turned the night sky into a database. Its robotic telescope in New Mexico methodically captured spectra from over 3 million galaxies, translating redshifts into distances. The resulting map looked like coral branching filaments of matter separated by dark caverns where almost nothing shone. SDSS made the cosmic web visible, an immense latticework where density fluctuates like pressure in a living lung. When Ryan Keenan, Amy Barger, and Lennox Cowie combined 2MASS infrared data with Sloan's optical depth, they could quantify the hollowness. Within a radius of roughly 300 million parsecs, about 1 billion light-years, the density of galaxies fell to roughly 80% of the cosmic mean. That 20% deficit sounds modest, yet in cosmology, it is extraordinary. A universe that is 99% empty by volume rarely tolerates differences that large on such scales. To confirm that the void was not an illusion created by dim galaxies hiding in the dark, the team turned to a different kind of cosmic yardstick, the explosions of dying stars. Type Ia supernovae occur when a white dwarf star steals matter from a companion until it reaches a critical mass and detonates. Because these cataclysms always ignite at nearly the same mass, their brightness is astonishingly consistent. Astronomers treat them as standard candles by comparing how bright they appear. How bright they ought to be, one can calculate distance with uncanny precision. Keenan's group collected every available Type Ia supernova within and beyond the suspected void, plotting their apparent brightness against redshift. The pattern repeated the galaxy count result. Nearby supernovae appeared slightly dimmer closer than expected, while those beyond several 100 million parsecs matched the global average. Space itself seemed to be stretching faster locally, as though gravity here had loosened its grip. Each method reinforced the others. galaxy counts, redshifts, and supernova distances all told the same story. The local universe is under dense, a gentle depression in the cosmic landscape. Even independent teams using radio telescopes to map neutral hydrogen, the 21-centimeter whisper of cold gas found the same thinning. Visualize it this way: the large-scale universe resembles a sponge or a honeycomb. The solid parts, the filaments and clusters, are thin walls of galaxies glowing where matter is pooled. The hollow bubbles between them are the voids, regions hundreds of millions of light-years across containing only a scattering of faint dwarfs. Our Milky Way rests on the inner slope of one of these bubbles, closer to its center than its wall. If you could travel outward for 1 billion light-years, you would cross a slowly thickening fog of galaxies until the count reached the cosmic average again. The sponge analogy is not poetic fancy. It arises from computer simulations of structure formation. In the early universe, matter was almost perfectly smooth, with tiny ripples in density 1 part in 100,000 visible today, as faint blotches in the cosmic microwave background. Over billions of years, gravity pulled the denser regions together while the emptier ones expanded faster. The result is a foam-like structure, dynamic and alive. The densest parts grow denser, the emptiest grow emptier. Voids are not holes carved out. They are spaces that expanded more rapidly than their surroundings. Our bubble, the KBC void, appears especially gentle. It does not end abruptly, but tapers like a valley whose slopes merge into distant hills. Its edges are defined by rich clusters, the Coma wall to one side, the Perseus-Pisces supercluster to another, the Shapley concentration further beyond. Their combined gravity forms the walls of our cosmic room. Inside, the pull is weaker, the light more widely spaced, and the average galaxy more solitary. For astronomers, measuring this hollowness is an act of patience. Every count must be corrected for brightness limits, dust obscuration, and cosmic evolution. Galaxies change over time. What looks underdense could simply be older, fainter populations. Yet after all corrections, the signature persists a 20% deficit in matter, sustained across a region nearly 2 billion light-years in diameter. That number 20% ripples through cosmology. It's large enough to affect how we infer distances, how we calibrate the Hubble constant, even how we estimate the universe's age. In regions of lower density, the expansion rate appears faster. In denser regions, slower. To someone observing from outside our bubble, the local universe might seem to breathe differently. Its tempo quickened by the quiet around us. Some physicists liken it to standing in the eye of a storm. The wind still moves, but the air feels calmer, less pressed. Others call it the Swiss cheese model of the cosmos, each void. A whole, each cluster a lump of cheese, the whole loaf expanding as one. From a certain distance, the pattern averages to smoothness. Up close, it's a riot of structure. The beauty of these surveys is that they allow us to see the pattern from both scales at once. When you step back hundreds of millions of light-years, the individual galaxies fade and the geometry emerges: filaments, glowing like nerves, voids dark like lungs between breaths. The cosmic web isn't random. It's an echo of physics itself, sculpted by gravity expansion and the invisible scaffolding of dark matter. And here we are, a spiral galaxy adrift inside one of its largest hollows, using the faint glimmers of others to measure the shape of our solitude. The void doesn't announce itself with borders. It reveals itself in statistics, in the missing light, the sparse galaxies, the slightly brighter supernovae that tell us space has stretched more than expected. The discovery does not make us central, only aware. We are the surveyors of absence, mapping the negative space of creation. To measure nothing is to learn how much something it takes to fill it. Next, we follow that light itself, the way it changes energy, as it crosses the hollow, and discover how the universe's oldest glow carries the fingerprints of emptiness across the face of the sky. Light, like truth, never travels unchanged. Every photon that reaches your eyes or a telescope's sensor carries the memory of every field of gravity it has crossed, each pull and push, written into its color. In the dense regions of the universe, gravity grips that light, stealing a little of its energy as it climbs away from clusters and filaments. Inside the voids, where gravity slackens, light loses less. And so, the universe, when seen through its oldest glow, begins to whisper a strange story. The light itself can lie about distance, age, and even speed, all because of where it has been. The principle seems simple. As the universe expands, space stretches every wavelength of light traveling through it, turning blue toward red, a cosmic Doppler effect we call redshift. The farther the light travels, the more stretched it becomes. This is how astronomers measure distance. The deeper the red, the farther the source. But redshift is not only the language of expansion, gravity can paint its own tints. When a photon climbs out of a gravitational well, say a galaxy cluster, it loses energy and shifts slightly redder. When it passes through a void, the opposite can happen. With less gravity to sap its strength, the photon retains a touch more energy, arriving a bit bluer, brighter, younger than expected. Now imagine this not as an isolated effect, but spread across billions of light-years of cosmic landscape. Light from the early universe, the cosmic microwave background, or CMB, has been travelling toward us for 13.8 billion years. On its way, it has crossed countless hills and valleys in the gravitational terrain of the cosmos. Dense clusters, empty voids, filaments stretched between them. Each crossing imprints a subtle change in the photon's energy, a ghostly fingerprint of the structure it encountered. This phenomenon is known as the integrated Sachs-Wolfe effect, named after Rainer Sachs and Arthur Wolfe, who predicted it in the 1960s. They realized that if the universe's expansion is accelerating as dark energy now drives it to do, then gravitational wells and voids don't stay constant. They evolve as light passes through them. A photon falling into a gravitational well gains energy, but as it climbs out, if that well has shallowed due to cosmic expansion, it loses slightly less than it gained. It exits with a net energy boost, appearing a bit hotter. Conversely, a photon crossing a void where gravity is weak emerges cooler, a tiny drop in temperature etched onto the CMB map. To see these minute shifts millionths of a degree, astronomers built satellites that stare at the microwave sky with impossible patience. NASA's Dome Map and later the European Space Agency's Planck mission measured the CMB's temperature at every point of the sky to microkelvin precision. What they found was a pattern both beautiful and unsettling, a patchwork of faint warm and cold spots scattered across the heavens. Most correspond to primordial fluctuations, ancient imprints from when the universe was young and nearly uniform. But some of those spots are far too large and too aligned with known cosmic structures to be accidents. One of them lies in the constellation of Eridanus, a massive, unusually cold patch spanning tens of degrees of sky. When cross-checked with maps of galaxy distribution from the Sloan Digital Sky Survey, that region lined up almost perfectly, with a super void hundreds of millions of light-years across. Light passing through that empty gulf had cooled just as Sachs and Wolfe predicted. The void left a literal shadow in the oldest light in existence. Other correlations followed. Each confirmed void, those traced by 2MASS SDSS and the Dark Energy Survey, seemed to echo faintly in the microwave background, a pattern of slightly cooler dots that betray the path of light through low-gravity regions. These are the fingerprints of emptiness, proof that the large-scale skeleton of the cosmos subtly reshapes the radiation that fills it. The effect is tiny, but in cosmology tiny means powerful. By stacking data from hundreds of voids, astronomers found a consistent signal. Photons that traverse under dense regions arrive cooler by a few microkelvin. It's a whisper of differential expansion, a testimony that space itself stretches faster inside the hollows. The universe's own light testifies to its unevenness. To visualize this, imagine the cosmic web as a vast terrain of hills and valleys. Clusters are mountains of gravity, voids are low plains. The CMB is like a rain of light falling across that landscape. Where it flows through valleys, it slows and cools. Where it runs over hills, it speeds and warms. By mapping these temperature ripples, scientists can reconstruct the hidden topography of matter and emptiness. But the light does more than reveal structure, it also distorts our measurements. When we use the brightness of distant galaxies or supernovae to gauge distance, we implicitly assume that the light travelled through average conditions. Inside the KBC void, those conditions are not average. Weaker gravity means photons experience less energy loss, so distant objects appear slightly brighter than they would from a denser vantage point. The cosmos tricks our rulers. A supernova that seems closer might actually be farther away, its light less tired from its journey through emptiness. Such biases feed directly into the Hubble tension, the conflict between the expansion rate measured locally and that inferred from the CMB. If our region of space allows light to travel with a little less gravitational drag, our instruments naturally record a faster apparent expansion. The universe hasn't changed, it's our laboratory that bends. For cosmologists, the CMB's delicate cool spots are more than curiosities. They're calibration marks on reality itself. They show that gravity expansion and light interact differently, depending on the density of space they traverse. Inside a void, time flows a hair faster, light runs a little freer, and the universe looks subtly younger. Think of it this way: the cosmic microwave background is the oldest photograph ever taken an image of the universe, when it was only 380,000 years old. But it's also a mirror, and when we look into it, we see not just the early cosmos, but the distortions of every structure the light has crossed since then. Each void, each cluster leaves a fingerprint on the portrait. Ours too must be there, a faint, cool imprint of the KBC hollow written across the background's silk-thin glow. In that sense, the universe carries its own record of absence. The light does not lie maliciously. It simply tells the story from its own perspective, a chronicle of the places where gravity was strong and where it nearly vanished. The challenge is learning to translate its dialect. When you stare at the CMB map, a mottled egg of red and blue patches, you're looking at a diary of the universe's uneven heartbeats. Some of those heartbeats come from far beyond, some from right here in the quiet bubble we call home. And each whisper of cooler light is a reminder that even emptiness leaves a trace, that even what isn't there still speaks. Next, we follow that bias of light into its consequence, the numbers themselves, and ask why two perfectly valid measurements of the universe's expansion refuse to agree. Every great theory begins to tremble not when it meets opposition, but when it meets precision. For a century, astronomers have been measuring how fast the universe expands, how quickly distant galaxies drift away from one another as space itself stretches. The answer should be singular. It defines the age of the cosmos, the scale of all distances, and the pace at which everything moves. But the universe, in its quiet mischief, has given us two answers. Both are elegant, both are backed by impeccable data, and they disagree. This is the Hubble tension, a polite term for one of the most persistent crises in modern cosmology. The number in question is the Hubble constant, the rate at which galaxies recede per unit distance, usually expressed in kilometers per second per megaparsec. The deeper a galaxy lies in the cosmic web, the faster its light stretches away from us. Measure that gradient and you can infer how quickly the universe as a whole is expanding. Simple in theory, maddening in practice. There are two primary methods to measure it. One looks outward, deep into the early universe using the ancient afterglow of the Big Bang. The other looks inward using nearby galaxies and supernovae as milestones. Each acts as a ruler carved from a different era of cosmic history. The Planck satellite launched by the European Space Agency in 2009 belongs to the first camp. By mapping the cosmic microwave background with exquisite precision, it captured a portrait of the universe as it was only 380,000 years old. From that baby picture, scientists can infer the cosmos's ingredients: dark matter, dark energy, baryonic matter, and run Einstein's equations forward to predict today's expansion rate. Planck's model yields a value of 67.04 or 66.5 km per second per megaparsec. The second method, pioneered by teams like GEOS, led by Adam Rees, measures expansion directly in the nearby universe. It builds a distance ladder, start with Cepheid variable stars whose rhythmic brightening reveals their true luminosity, use them to calibrate Type Ia supernovae, then measure the recession speeds of galaxies hosting those explosions. The result, a faster expansion around 73 + 1 km per second per megaparsec. Two methods, two epochs. Both precise, both internally consistent, and separated by a stubborn 9%. In everyday life, a 9% discrepancy is small. In cosmology, it's a rift deep enough to question whether our model of the universe is complete. If Planck is right, the universe is about 13.8 billion years old. If the local measurements are right, it's closer to 12.7 billion. That difference of more than a billion years would rearrange cosmic chronology. When the first galaxies formed, when stars lit the darkness, even how long heavy elements had to brew before life emerged. It's not just a matter of numbers, it's a matter of history itself. Scientists have spent the last decade auditing every rung of the distance ladder, every calibration constant, every assumption baked into the equations. Could the early universe inference be missing some unknown particle that changed expansion shortly after the Big Bang? Could the late universe observations be skewed by unrecognized biases in the local cosmos? Or could both be right, each describing a region of the universe that expands at a slightly different tempo? That last idea is where the KBC void slips quietly back into the frame. If our galaxy resides inside a large underdense region, then the local rate of expansion would naturally appear higher. In a space with less matter, gravity's inward pull is weaker, allowing expansion to run ahead by a few percent. Observers inside that bubble would measure galaxies receding faster than the global average, even though the universe as a whole expands uniformly. This is what cosmologists mean by local bias, the difference between what the universe does everywhere and what we observe from our specific location within it. It's a reminder that our instruments, however precise, still share our cosmic address. We're inside the experiment. Think of it as weather versus climate. The global climate of the universe is defined by the cosmic microwave background, broad, steady, predictable. But our local weather inside this supervoid may be slightly warmer, slightly windier, skewing the readings. The Planck result tells us the average climate of the cosmos. The local supernova and CFID data record the weather of our neighborhood. Both are true, but they are not the same. If the KBC void accounts for even a portion of the tension, say 2 or 3% of the difference, it would still leave a residue unaccounted for a gap large enough to imply new physics. Some have suggested evolving dark energy sterile neutrinos or changes in how gravity behaves across vast scales. Others warn against premature revolution. The void might be bigger or emptier than we think, or our measurements more tangled than we realize. The irony is almost poetic. For centuries we fought to remove ourselves from the center of the universe. Now our measurements depend precisely on where we stand. The cosmological principle tells us that every point in the universe should be equivalent, but the data whisper that ours might not be. In a cosmos 93 billion light-years across, we may simply occupy a slightly lighter patch of its fabric, and that lightness shifts the rhythm of expansion we hear. Picture 2 clocks ticking in different rooms. Both are built perfectly, but one stands on a floor that flexes. Over hours, the difference is invisible. Over years, it widens. The Planck clock ticks to the beat of the whole universe. The Everest clock ticks within the flexible floorboards of our local void. Their times disagree not because one is broken, but because their flaws are different. For cosmologists, the question is whether the flaw matters. If the Hubble tension comes purely from local bias, then the foundations of LCDM, the lambda-cold dark matter model, remain intact. But if the difference persists even after accounting for bias, the pillars of modern cosmology may need rebuilding. Either outcome carries beauty. One reaffirms the coherence of Einstein's universe. The other invites us to expand our imagination of what space and time can be. For now, the debate remains unresolved. New instruments, the Vera Rubin Observatory, Euclid, the Nancy Grace Roman Space Telescope will soon measure galaxies and supernovae across far larger volumes, smoothing out local anomalies. If the gap survives those tests, we will know the discrepancy is not in the data, but in our understanding of the cosmos itself. Until then, the universe holds its two truths side by side, one written in the fading microwave light of its birth, the other in the fresh starlight of its present. Between them lies a 9% question, a silence that stretches across billions of years, waiting for us to listen carefully enough to hear which clock is telling the true time. Next, we step deeper into the void itself and learn what it means to take measurements from a moving laboratory, how our very vantage point may warp the numbers we trust. Every measurement we make of the cosmos begins here inside a bubble that is itself moving, stretching, and subtly uneven. We build our instruments on Earth inside the Milky Way, which drifts inside a local group which sails within the faint depression of the KBC void. It is like doing oceanography from within a wave. The surface you float on is never truly still, yet you try to measure the sea as though it were. To understand how this distorts our cosmic rulers, imagine two observers. One lives far outside the void where matter density matches the cosmic average and expansion proceeds at the global rate predicted by Planck's data. The other, us, resides within the underdensity where gravity's pull is weaker and expansion runs slightly ahead. Both look outward, both measure the redshift of galaxies, but they inhabit different frames of reference. The one outside stands on the calm plateau, the one inside rides the swell. From the interior of the void, light from distant galaxies seems to stretch faster because the space it travels through is itself expanding more rapidly than the universal mean. When we calculate distances using that light, we overestimate the pace of cosmic growth. Every rung of the distance ladder confides. Type a supernovae surface. Brightness fluctuations rests on assumptions about how much space expands per unit of time. But if our local patch breathes faster, each rung tilts slightly upward. The ladder itself is curved. Astronomers account for local motions by mapping the peculiar velocities of galaxies, their deviations from pure Hubble expansion. We correct for the pull of the Virgo cluster, the great attractor, the Shapley concentration. Yet these are only the denser structures. The void's influence is subtler. Instead of pulling, it releases. Galaxies near the center of an underdensity drift outward, carried by the faster local expansion. From our position, this looks like an extra redshift, a slight acceleration of everything around us. The effect is small, but it biases the slope of the line we draw when plotting distance versus velocity. In cosmological terms, this is a reference frame distortion. Space inside a void isn't just emptier, it evolves differently. The local scale factor, a local t is a local gene c, a local t, grows faster than the global a global, ta, global t a global t. When we convert redshifts to distances, we implicitly assume a single scale factor, but the universe offers many. Observers in dense clusters and those in deep voids inhabit slightly different versions of cosmic time. Their clocks tick at different rates, their rulers stretch at different speeds. To visualize this picture, the universe is a rolling ocean of space-time. The dense filaments are troughs where gravity gathers matter. The voids are crests where expansion surges. Every observer floats somewhere on this moving surface. The one atop a crest, the void dweller feels the world rise beneath them. To measure the ocean's average level, they must remember that their vantage point is elevated. Failing to do so makes the sea seem deeper, the waves steeper, the motion faster than it truly is. In practice, this bias threads through all local measurements. When astronomers calibrate Cepheid variables, they assume the same period-luminosity relation applies everywhere. But Cepheids in nearby galaxies, those inside the void, may sit in a slightly different cosmic environment, where expansion history and metallicity differ subtly. The next step, using Type Ia supernovae to gauge distances out to hundreds of megaparsecs, inherits that calibration. Each rung compounds the earlier bias. By the time we reach the scale where the KBC void fades into the denser universe, our inferred Hubble constant has drifted upward, a reflection of where we are rather than how the cosmos truly expands. The irony is that general relativity already allows for such local variations. Inhomogeneous solutions to Einstein's equations, called Lemaitre-Tolman-Bondi LTB models, describe spherical regions of differing density embedded in an expanding universe. In these models, an observer at the center of an underdense region would measure a higher local expansion rate exactly as we do. The math says the effect could reach several percent enough to explain part but not all of the Hubble tension. The trouble is that we don't yet know how far the bias reaches. Our telescopes can see only the observable universe, and within it we can map perhaps a few thousand well-measured supernovae. That's like judging the shape of the ocean by watching a handful of waves. To remove the bias, we'd need to compare observations from many voids and clusters across the sky, a kind of cosmic triangulation that no single observer can perform. Still, simulations help. When cosmologists model a universe filled with voids and filaments, they see the same phenomenon observers inside underdense regions consistently record higher apparent Hubble constants. The pattern is not random, it's geometry. Each void expands faster than its surroundings, pushing matter toward the walls and carrying its inhabitants outward like passengers in a swelling balloon. From within, everything seems to be accelerating away. From outside, the void simply breathes. That breathing carries through every wavelength we measure. Microwave photons passing through our local underdensity arrive slightly cooler. Infrared surveys find fewer galaxies than average. Even gravitational lensing, the bending of light by mass, shows weaker curvature here than in denser regions. Our laboratory, in other words, is not anchored. It drifts within a moving medium of space-time. The consequence is both humbling and exquisite. The numbers we treat as universal constants, the Hubble constant cosmic age density parameters, are not measured from nowhere. They are measured from here. Every data point carries the echo of our cosmic neighborhood. The void is not merely a backdrop. It is part of the experiment. To correct for that bias, astronomers now model expansion as a layered phenomenon, a local bubble expanding faster nested within a slower global universe. The transition zone where density climbs back to average acts like the shoreline of our cosmic island. Beyond it, the expansion rate settles toward the global value measured by Planck. Within it, we remain the moving laboratory, our instruments swaying gently with the tide. Perhaps this is the deeper lesson of the Hubble tension, not that one side is wrong, but that both are right from where they stand. The universe is not a single rigid frame. It is an ocean of frames, each shaped by the density beneath it. When you gaze into the night sky, you're seeing across those moving surfaces waves of space-time rising and falling, carrying light from distant shores. Our task is to learn the rhythm of that motion, to know when the sea itself is lifting us, and when we are finally measuring the ocean, not the wave. Next, we follow that motion outward to the stretched edges of the cosmic fabric itself, and see how low-density regions like ours deform the very structure of space, making the universe's expansion a living, breathing thing. In the deepest darkness of the digital universe, supercomputers spin entire cosmoses into being. Line by line, particle by particle, they recreate billions of years of gravitational choreography, condensing the laws of physics into slow-motion creation. These are the Millennium Illustris and Eagle simulations, immense numerical experiments that let us watch how the universe builds itself from near nothing. And when they are set free to evolve, one pattern appears again and again, emptiness grows. The dense regions gather, but the hollow ones expand faster, their edges swelling like bubbles in a loaf of rising bread. In the Millennium simulation, completed in 2005 by the Max Planck Institute, 10 billion dark matter particles filled a cube of virtual space 2 billion light-years wide. At the start, the distribution was almost uniform, echoing the smooth microwave background of the early cosmos. As gravity went to work, tiny overdensities collapsed into filaments while underdensities relaxed and stretched. By the end of 13.7 billion years of simulated time, the volume of space occupied by voids had grown to dominate everything, about 90% of the total. The dense knots, though dazzlingly bright, became mere punctuation marks between the hollows. Later projects like Illustris and Eagle added the missing ingredients: gas physics, star formation, feedback from supernovae and black holes, radiation magnetism. They showed that baryonic matter, ordinary atoms, rides the scaffolding of invisible dark matter, lighting up its densest creases while leaving the vast gaps unlit. The equations of general relativity applied statistically through Newtonian approximations revealed a simple truth: where there is less matter, there is less resistance to expansion. The cosmic fabric stretches most easily through its thinnest threads. Picture space-time as a vast sheet woven from elastic filaments. In regions rich with galaxies, the weave is taut. Gravity tugs at every strand, keeping them close, resisting the pull of cosmic acceleration. Inside a void, the threads loosen. Dark energy finds less opposition there and pushes outward more freely. The result is differential growth, a universe that doesn't expand uniformly, but ripples breathing faster through its hollows. In visualizations from these simulations, you can see it happen. The early cube of matter looks like faint static, nearly uniform grey noise. As time passes, that noise condenses into filaments and walls. Between them, spherical cavities bloom, merging into complex interconnected tunnels. The densest clusters become nodes where thousands of filaments converge. The void's vast pools of near-nothing inflate until they touch. When they do, the boundaries thin and burst, forming even larger bubbles. The process never stops. Voids don't merely persist, they drive the large-scale expansion, channeling dark energy's work. In the Eagle simulation's final frames, the contrast is startling. The voids glow faintly blue in density maps, cool and diffuse. The filaments blaze golden with galaxies. Expansion has not only stretched the fabric, but warped its tension. Where mass is concentrated, space curves sharply. Where it's scarce, the curvature softens like a drumhead, losing tautness at its edges. These digital universes confirm that underdense regions behave like miniature accelerators. Their internal Hubble rates can be several percent higher than the cosmic mean, depending on how empty they are. It's not magic, it's geometry. In Einstein's equations, the rate of expansion h depends on the balance between energy density and curvature. Lower density means lower deceleration, so the local scale factor at grows more quickly. The simulations render this abstract math in motion the fabric of space loosening wherever it thins. If you could touch that fabric, it would feel like silk drawn over air. Dense clusters pull it tight, their gravity gathering the threads into knots. Voids, by contrast, are places where the weave relaxes, where dark energy seeps between the fibers and pries them apart. Each photon traveling through this landscape follows the subtle sag of the weave, its path deflected not by walls, but by the gentle outward bulge of nothingness. There is poetry in the numbers. The Millennium team computed that a typical large void expands about 10–15% faster than the cosmic average. Over billions of years, that difference compounds, turning a modest depression into an enormous bubble. Two adjacent voids merging create an even larger region of a low density, the cosmic equivalent of soap bubbles fusing on the surface of water. When the simulations are run forward into the future, they predict a haunting outcome as dark energy continues its steady push. The filaments will thin, the walls dissolve, and the universe will become an archipelago of isolated islands drifting in an ever-widening sea. This vision redefines what empty means. A void isn't a lack of substance, it's a dynamic player in the cosmic drama. The simulations show that the expansion of space itself is a feedback process. Gravity shapes matter, matter resists expansion, and expansion stretches the regions where matter is absent, creating more voids still. The universe, in other words, organizes its own looseness. Think of a woven cloth suspended from all sides. If you pull evenly on it, every thread shares the strain. But if certain areas are already thin, they stretch first, taking more of the tension. The overall fabric doesn't tear, it breathes unevenly. That's what dark energy does to the cosmic web, a uniform push acting on an uneven texture. The voids already light yield more, the clusters heavy with galaxies barely move. The result is a living fabric under stress, rippling with asymmetry, forever redistributing tension. Inside these simulated universes, we can even watch the birth of regions like the KBC void. Slight underdensities in the early matter field, only one part in 10,000 weaker than their surroundings, blossom into cavities hundreds of millions of light-years wide. By the time the simulated universe reaches its present age, the observer at the center of such a void would measure precisely what we do: a higher local Hubble rate, fewer galaxies per volume, a quieter gravitational landscape. In that sense, the computer cosmos and the real one agree. The voids are not anomalies, they are inevitability's side effects of gravity's own success. The denser regions feed on mass, pulling it inward, while the spaces between are left to drift and swell. Over cosmic time, matter flows out of the voids like air from a punctured balloon, further lowering their density and accelerating their growth. The expansion we observe locally may simply be the echo of that slow, inexorable exhalation. Pause and picture it one last time. Space is not a static grid, but a living cloth, its weave stretching and relaxing. Galaxies are beads sewn along the seams, sliding outward as the thread lengthens. Between them, the emptiness hums a quiet engine of expansion. And somewhere within that vast textile lies our own galaxy, adrift in a patch of loosened weave, our laboratory stitched into the fabric it is trying to understand. Next, we follow this pattern to its natural consequence: how two universes, the local and the global, can coexist in the same cosmos, both true within their frames, both shaped by the rhythm of expansion that varies across the web of emptiness and matter. There are, in a sense, two universes not separated by space, but by perspective. One is the local universe, the realm we inhabit and measure with light from nearby galaxies, Cepheid variables and supernovae, an intimate cosmos stitched together by the data of the last few 100 million light-years. The other is the global universe, visible through the cosmic microwave background, a vast canvas frozen when the cosmos was only a child. Both are real, both are accurate within their frames of reference, and yet when they compare notes, their numbers refuse to match. The local universe speaks in the language of direct observation. Teams like Shade0ES, led by Nobel laureate Adam Riss, use the nearby cosmos as a living ruler. They measure pulsating Cepheid stars whose rhythm of brightening reveals their true brightness, and use those stars to calibrate Type Ia supernovae, whose explosions act as cosmic lighthouses visible across billions of light-years. From those steps arises a simple relation: distance versus redshift, speed versus separation. It is the heartbeat of expansion itself. Every data point in Rees's chart is a galaxy receding from us, its light stretched by the swelling of space. Plot enough of them, fit a line through the scatter, and the slope gives you the Hubble, constant a snapshot of how fast the universe is expanding right now. The result, refined again and again through thousands of observations, hovers near 73 kilometers per second per megaparsec. The global universe, meanwhile, speaks in a different dialect, the dialect of ancient light. The Planck satellite, orbiting 1 million miles from Earth, measures the cosmic microwave background CMB, the oldest radiation still visible. It is a fossil record from 13.8 billion years ago, encoding the physics of the early universe, how matter and radiation rippled, how gravity sculpted those ripples, and how expansion froze them in place. When cosmologists fit these ripples to Einstein's equations within the framework of LCDM lambda cold dark matter, they can run the universe forward in time like a simulation and calculate how fast it should be expanding today. That answer, 67.4 kilometers per second per megaparsec, is exquisitely consistent precise to less than 1%. 2 lenses, 2 epochs, 2 truths. At first glance, it seems one must be wrong. If both methods are sound, the cosmos can't be expanding at 2 different rates. But that reasoning assumes that both observers inhabit identical patches of space-time, an assumption the KBC void calls into question. Inside a large underdensity, the local expansion rate naturally runs faster. Think of space as dough rising in an oven. The thin parts expand first, the thicker crust lags behind. The baker's thermometer reads one temperature, but the bread swells unevenly. The CMB-based measurement samples the average dough, while the supernova-based one samples the airy interior around us. Each is accurate within its context. They differ because their contexts are not the same. Adam Rees himself has often emphasized this humility. The universe isn't a single experiment, he told a symposium in 2022. It's a collection of different epochs and conditions. We're taking its pulse in 2 different rooms of the same house. In other interviews, he likened the measurements to 2 thermometers placed in different parts of a kitchen. One in the oven, one on the counter. Both are correct readings, but they describe distinct environments. Rees and his collaborators continue to refine the local ladder, checking every calibration step, cross-matching C-feeds, with parallax distances from Gaia, testing supernova brightness models, even measuring expansion using red giant stars as alternative candles. Each refinement tightens the error bars but leaves the result essentially the same: the local universe expands faster. We've tried to make it go away, Rees joked in a NASA briefing. It just won't. Meanwhile, cosmologists working with Planck and other CMB data stand equally confident. Their model, tuned by the early universe's radiation, has predicted countless other phenomena: the abundance of light elements, the clustering of galaxies, the age of star populations with uncanny precision. If their expansion rate were wrong, many of those predictions would unravel. The model's success argues that the CMB value must be close to the truth for the universe as a whole. So both camps look at the same cosmos through different windows. One sees now, the other sees then. And perhaps the tension between them is not contradiction, but parallax, a shift born from perspective. The dual universe idea finds support in relativistic cosmology itself. Einstein's equations allow space to evolve differently in regions of varying density. Observers inside a void experience a distinct curvature of space-time. Their cosmic time runs a little ahead of the global average. When they measure redshift and distance, they translate that local curvature into a slightly higher expansion rate. To them, galaxies truly appear to recede faster. To an observer outside, they do not. Both are right. The difference is not error, it's geometry. The simulations back this up. When models like Illustris or Eagle are run with observers placed in underdense zones, the synthetic astronomers measure local Hubble constants just as elevated as ours. When the same simulation is sampled from a denser filament, the value drops to match the CMB prediction. The cosmos in these digital experiments becomes self-consistent, but non-uniform, a quilt of micro-universes stitched together by relativity. If that picture is true, then the Hubble tension isn't a crisis, but a revelation. It shows that cosmic expansion is not a single tempo drummed into uniformity, but a symphony played on many instruments. The CMB gives us the global melody. The local supernova capture the brighter, faster variation near our seat in the orchestra. Still, even Rees admits the possibility that the difference could hint at deeper physics. It's entirely possible that both are right, and yet the universe contains new ingredients we haven't imagined, he said. That's what makes this exciting. A 9% mystery is the kind we can actually solve. Between the numbers lies a quiet philosophical shift. We are learning that objectivity in cosmology is not freedom from perspective, but awareness of it. The universe does not present one truth, but a family of truths, each honest within its coordinates. The global model tells us how the cosmos behaves in the average sense across all of space and time. The local model tells us how it behaves here and now. Reconciling them may not mean forcing them to agree, but understanding how both can coexist within Einstein's curved reality. If the fabric of space can stretch differently in different places, then the cosmos is both one and many a dual universe layered and alive, bound together by light that carries the stories of all its regions at once. Next, we descend one level deeper into that relativity of place and time, exploring how gravity's weakness inside a void affects the very ticking of cosmic clocks, the slow, almost imperceptible difference in how time itself moves. Time to us feels absolute. It hums forward like a steady current, impartial and invisible. Yet physics whispers something subtler. Time depends on where you are and how much gravity holds you. Inside a mountain's heart, seconds crawl a little slower. High above the clouds, they drift a touch faster. Even the Earth's gentle pull creates measurable differences in the ticking of atomic clocks' nanoseconds over the span of a day. And across the immense landscapes of the cosmos, where gravity itself ebbs and flows, with the distribution of matter, that difference becomes part of the universe's hidden rhythm. To live inside a void is to live where gravity is weakest. There is less mass to curve space-time, less potential energy to hold clocks back. And so within these great hollows, the KBC void included time runs slightly faster than it does in denser regions of the universe. It's not something anyone could ever feel. The change is measured not in seconds, but in the faint skew of light's colour and the minuscule drift of cosmic rulers. Yet to the precision-obsessed eyes of cosmology, that small advantage of time is profound. Einstein's general relativity teaches that the rate of a clock depends on its gravitational potential. The deeper the potential, well, the closer you are to a mass concentration, the slower your clock ticks relative to one far away. This effect, called gravitational time dilation, is not fiction. It's the reason GPS satellites must correct for relativity, so that navigation systems on Earth remain accurate. On a cosmic scale, where clusters of galaxies are the mountains and voids, the valley's inverted time dilation sculpts an uneven temporal landscape across the universe. But inside a void, the relationship flips. Because gravitational potential there is higher, less negative, less curved clocks speed up slightly, compared to those anchored in denser clusters. A second here is not precisely the same as a second there. The difference is infinitesimal on human terms, yet when translated across billions of light years and billions of years, it accumulates into a measurable bias. This is sometimes called gravitational time dilation reversal, not because physics inverts, but because the context changes. In clusters, gravity slows time. In voids, the absence of gravity lets it flow more freely. Two observers synchronized at the dawn of the universe would end up out of step today if one drifted into a dense supercluster while the other remained in an underdensity. The void dwellers' watch would be ahead, recording a slightly older age for the cosmos than their counterpart in the web's crowded knots. This subtle, temporal divergence lies at the heart of what cosmologists call inhomogeneous time flow. It's the quiet partner to the Hubble tension, the possibility that part of our measurement bias arises not only from expansion differences, but from how we experience time itself. In simplified cosmological models, the so-called Friedman, Lemaitre-Robertson-Walker universe, space and time stretch together uniformly. But in a universe textured by voids and filaments that synchronization breaks. Imagine the cosmic fabric again stretched taut across the framework of dark matter. Where galaxies cluster, the fabric dips. Time pools, they're slow and heavy. Where voids swell, the fabric rises. Time slides more easily across its surface. Photons traveling through this uneven field accumulate or lose infinitesimal fragments of energy, subtly changing their frequency, and thus the apparent distance we infer from their redshift. In this way, even time dilation becomes a participant in the illusion of a faster expanding local cosmos. In practical terms, the effect nudges distance calibration, the invisible backbone of cosmology. When we use standard candles like Type Ia supernovae to chart the Hubble expansion, we assume a universal rate of time that light curves decay rates and brightness histories unfold the same way everywhere. Yet the ticking of physical processes, radioactive decay, thermonuclear burning, depends on time's local tempo. Inside a void, those processes would very subtly appear to evolve faster. Their light curves would compress their apparent brightness shift. If we ignore that variation, we slightly misjudge how far they are. A cosmic second that's just a little too quick translates into a universe that looks a little too young, a little too eager to expand. Astronomers compensate for many relativistic effects peculiar velocities, gravitational lensing, dust attenuation, but gravitational potential bias remains difficult to isolate. We can't easily compare clocks between galaxies, and no single photon carries a tag that says how gravity treated it along the way. Instead, cosmologists rely on averages, building statistical corrections into simulations and models. Still, even in those models, voids make their mark. The Millennium and Eagle simulations, when adjusted for local potential differences, show a slight acceleration in the passage of cosmic time within underdensities, amounting to a discrepancy of several tens of millions of years over the age of the universe. Philosophically, it is a strange thought that here in this quieter corner of existence, we might live a little ahead of the cosmic clock. Our galaxies drift in faster flowing time, our telescopes observe the universe aging at a slightly different pace than it does elsewhere. In an infinite cosmos, there is no single heartbeat, only a shimmering web of tempos, each set by its gravity. One can think of it like the ocean waves of earlier analogy. The peaks move swiftly, the troughs lag behind. The crests are voids, are lighter, thinner, rising faster with the cosmic tide. The valley's dense clusters sink deeper into gravity's pull, their internal clocks slowed by the weight of their own matter. The universe seen this way is not a single metronome, but a symphony of shifting rhythms, every region marking time in its own key. To us, of course, it feels seamless. Our hearts beat, our atoms vibrate, our watches tick, without knowing that in a distant cluster, the same second would be just a whisper longer. But when we look across the abyss, when we use those distant clocks to judge distance and history, we must account for this invisible drift. Otherwise, the universe we reconstruct will always seem slightly misaligned, like two films projected out of sync by a few frames. This is the quiet conspiracy of time inside a void. It lends speed to light, haste to expansion, and illusion to our measurements. It is not error but perspective, another reminder that the observer and the observed are woven together by the same elastic clockwork. In the next part, we turn from these invisible flows of time to the breathing of the universe itself, the way matter and emptiness cooperate like lungs to sustain the rhythm of expansion across the cosmic web. The universe breathes, not with air or lungs as we know them, but with the slow, rhythmic expansion of its very fabric. Across billions of light years, matter drifts and flows, inhaling into clusters, exhaling through voids. The filaments and walls of galaxies act like the ribs of a cosmic chest, while the vast empty regions between them, those immense hollows we call voids, serve as the universe's lungs. And right now, those lungs are exhaling. Everywhere we look, galaxies inside these underdense regions are quietly moving outward, sliding away from the centers of the voids as though pushed by an invisible hand. It's a strange sight. Gravity, the eternal puller, seems to reverse itself. Instead of drawing matter inward, it appears to drive it outward. Cosmologists call this motion gravitational outflow, a phrase that captures both the paradox and the poetry of what's happening. To understand it, imagine the universe as an ocean of matter. In some places, the water is thick with galaxies. In others, it's thin, nearly dry. Gravity pulls more strongly where the density is greater toward the crowded regions, so material from the sparse zones naturally drifts outward, pulled not by the emptiness itself, but by the heavier surroundings. In effect, the void center is being evacuated, its contents siphoned away toward the dense walls that frame it. This outward drift can be hundreds of kilometers per second, measurable through the Doppler shifts of galaxies. Observations from the Cosmic Flows 3 catalogue, compiled by Brent Tully and collaborators, map this invisible current. In their charts, the local void, our own, pushes galaxies outward, while the Shapley supercluster, a dense wall far beyond, tugs them from the opposite direction. Our Milky Way floats between these two vast influences, pulled and repelled, inhaled and exhaled, part of a vast galactic respiration. In the great cosmic simulations, Illustrious Eagle and Millennium, this breathing becomes visible. As billions of virtual years pass, filaments thicken and contract like sinews, while the interiors of voids grow and merge. Matter drains from their centers like mist dissolving from a clearing valley at dawn. What looks like a push is really a consequence of imbalance. The dense regions possess greater gravitational weight, so matter falls away from the void's low-pressure heart. The void expands not because it exerts a force, but because nothing within it is strong enough to resist. Yet to an observer inside the void like us, the effect feels inverted. Galaxies all around appear to recede from a central point. Gravity, which everywhere else binds here, seems to release. The local expansion accelerates the distances between galaxies grow faster than average. Space itself seems to open its lungs wider in the absence of mass. Mathematically, this gravitational outflow can be traced through the gradient of the potential field. In a void, the gravitational potential is relatively flat in the center and steeper near the walls. The slope points outward, so any object not perfectly balanced drifts toward the boundary. This creates a velocity field with vectors radiating from the center, a kind of invisible wind. Observations back this up. The Betty void, 330 million light-years across, shows galaxies near its edges moving outward at about 230 kilometers relative to its center. Similar flows have been measured in the Eridanus supervoid and even around our KBC void, where the local expansion exceeds the cosmic average by roughly 6–10%. These motions recorded in galaxy surveys like TUMAS and SDSS form a striking pattern. Space breathes faster where it is emptier. It's tempting to say gravity pushes here, but that's not quite true. Gravity only pulls, yet in the uneven fabric of space-time, a pull from every side except one behaves like a push. The result is the same galaxies accelerate away from the void's heart. Cosmologists sometimes call this effect a repeller, the gravitational counterpart to an attractor like the Shapley concentration. Together, attractors and repellers sculpt the cosmic landscape, guiding the flow of galaxies across hundreds of millions of light-years. From our vantage point inside this dynamic web, the motion is delicate but relentless. Over eons, the matter streaming from voids thickens the filaments, which in turn feed clusters where galaxies collide and merge. The universe's large-scale structure is not static, it is a living metabolism. Voids are not the absence of action. They are the lungs through which the cosmos renews itself. As dark energy stretches space, voids expand, and their expanding walls shepherd matter into ever more intricate forms. Picture the process on a human timescale. If you could speed up cosmic history and watch 1 billion years pass in a heartbeat, you'd see the universe inhale and exhale like some vast creature sleeping beneath its own stars. Filaments pulse inward, voids swell outward. The pattern repeats endlessly, diffusion and contraction in perfect counterpoint. We are not outside of this rhythm. We are inside its chest cavity, listening to the quiet thrum of its breath. Astrophysicist Thomas Buchert at the University of Lyon once described it simply: voids are the places where cosmic acceleration hides. In those airy interiors where gravity's grip is weak, the expansion of space itself dominates, mimicking a kind of anti-gravity. But it's not dark energy alone doing the work. The geometry of matter, its uneven distribution, creates this apparent repulsion. Gravity stretched thin yields to the push of the vacuum. So when you look at the cosmic web, the shimmering filaments of galaxies and the silent caverns between them, you are seeing a living anatomy. The clusters are the muscles, the voids the lungs, dark energy the breath that moves through them all. Each expansion, each outflow, each drift of galaxies away from one another is part of that grand respiration. And as with every breath, there is a rhythm to it, a balance between what contracts and what releases. The cosmos, it turns out, is not a still photograph, but a living organism inhaling matter into gravity's embrace and exhaling it into the quiet infinity of space. Next, we turn to how this ceaseless breathing, the outflow from the voids, reshapes the future of the cosmic web itself, hinting at a time when the universe's lungs might exhale for the last time, and the filaments between galaxies grow too thin to hold. There comes a frontier in the universe where gravity surrenders, not with a crash or a boundary line, but through quiet exhaustion, its pull stretched thin until the opposing tide of expansion takes over. That invisible frontier lies not in the heart of galaxies where gravity reigns absolute, but in the vast dark chambers between them, the cosmic voids. Everywhere in the cosmos, two forces share the stage. One is gravity born from mass and curvature, forever pulling matter inward, knitting stars, clusters and filaments. The other is dark energy, a mysterious pressure woven into the fabric of space-time itself, forever pushing outward, accelerating expansion. For most of cosmic history, gravity led the dance. But as the universe aged, its matter thinned and its expansion quickened. Now the two are nearly equal partners, and inside the voids that partnership breaks down into something closer to a truce. In the emptiest regions where matter density falls below, about 20% of the cosmic mean gravity's potential wells become shallow. The curvature of space-time flattens, the very geometry that once tugged on matter relaxes. Equations that describe expansion, The Friedmann equations derived from Einstein's general relativity reveal this precisely. They contain two terms, one for matter which slows expansion and one for dark energy which speeds it up. As density drops, the matter term fades, leaving only the acceleration term to dominate. The result is a patch of the universe where space itself stretches freely faster than the cosmic average. In these hollows, you can think of gravity as losing its conversation partner. It whispers into silence with no mass around to answer. The gravitational attraction between galaxies becomes too weak to resist the uniform pressure of dark energy. Galaxies drift apart not because something pushes them, but because the stage beneath them expands. And this is not just a poetic image, it is measurable. Observations of supervoids show internal expansion rates up to 20% faster than surrounding regions. Within the Eridanus or KBC voids, the balance tips unmistakably toward acceleration. To visualize this equilibrium, imagine a delicate tug of war. On one end, gravity holds the rope representing the combined mass of galaxies and dark matter. On the other, dark energy pulls not from a single point, but from everywhere at once, like a vacuum expanding from within the rope's fibers. As the void grows emptier, gravity's side of the rope slackens. The pull remains, but there's nothing left to grip. Eventually the rope stops moving, the cosmic equivalent of stalemate. From that moment on, the expansion runs away unchecked. Astrophysicist Thomas Buchert of the University of Lyon calls this threshold the zero-gravity surface, the point where the inward acceleration from mass exactly equals the outward acceleration of dark energy. Beyond it, the balance shifts permanently. Every void contains such a surface surrounding a small region still faintly bound. Outside that, core dark energy rules. The universe's large-scale structure can thus be seen as a vast mosaic of these zones, tiny islands of gravitational coherence surrounded by oceans of accelerating space. If we could trace this balance across the cosmic web, we'd see it fluctuate like a heartbeat. In the filaments, gravity's rhythm is strong. Galaxies merge, clusters coalesce, step outward into the walls and the pulse weakens, cross into the void and suddenly the rhythm reverses expansion, overtakes attraction, and the beat of the cosmos quickens. The voids breathe outward, the filaments strain to hold them back. It's an uneasy coexistence, each force defining the other. This shifting boundary has profound consequences. It means that over time the universe's structure is not just expanding, but dissolving. The zones where gravity still binds will shrink. The cosmic web's filaments will grow thinner, their bridges breaking one by one. The Milky Way and Andromeda, still destined to merge billions of years from now, will remain bound, but beyond our local group, everything will drift beyond reach. The voids, swelling under dark energy's dominance, will become the default landscape of existence. The Dark Energy Survey and Euclid mission both map this slow invasion of emptiness. By observing the shapes and motions of galaxies across cosmic time, they can pinpoint where the balance between matter and dark energy shifts. The results already hint at a gradual transition. Inside the largest voids, expansion dominates today. Near dense clusters, gravity still resists. The cosmos is in effect a patchwork of physical regimes, pockets of Newtonian pull embedded in a relativistic sea of acceleration. And yet the physics remains consistent. Einstein's equations still hold. They merely express different outcomes depending on the ratio of mass to energy. In the densest zones, curvature pulls inward. In the emptiest, it curves outward. Between them lies a thin interface, a cosmic twilight where the two cancel in a fragile stillness. If we could stand on that threshold midway between a galaxy wall and a void center, we would see two opposing destinies unfold. Looking toward the cluster, galaxies would appear to drift inward, gravity's dominion still intact. Looking toward the void, the fabric of space would seem to stretch beneath us, galaxies sliding away faster with distance. That invisible midpoint, the edge of gravity, is where the universe's future is decided moment by moment, breath by breath. So as the cosmos continues its quiet exhalation, remember that every star, every galaxy, and every atom of dust lives in negotiation. Gravity holds us close. Dark energy pulls us apart. Between their forces lies the fragile equilibrium that allows structure to exist at all. The voids remind us that this balance is temporary, a fleeting truce in an endless expansion, and someday when the universe's lungs grow too large and gravity's whisper too faint, even that truce will break. In the next part, we follow that trajectory forward to the far future, when the cosmic web finally tears loose from its own gravity, and the night between galaxies becomes infinite. If you wish to understand the universe, you must learn to map its silences. Galaxies are easy to see, bright, proud, and vocal, but the true structure of the cosmos hides in what isn't there. The vast cavities between clusters, the nearly invisible corridors of low-density space, the immense hollows where gravity yields to expansion, these are the canvases on which the cosmic web is painted. To chart them is to trace the skeleton of reality itself. Over the last decade, astronomers have begun a remarkable new enterprise mapping nothing. Their tools are the great sky surveys of our time, the Dark Energy Survey DES Euclid, the Vera C. Rubin Observatory's legacy, Survey of Space and Time LSST, and the James Webb Space Telescope JWST, each a different kind of cartographer together building a three-dimensional atlas of absence. The Dark Energy Survey, operating from Cerro Tololo in Chile, was the first to make the void visible in detail. Between 2013 and 2019, its 470 megapixel camera photographed 300 million galaxies across 1/8 of the sky, capturing their shapes and clustering with exquisite precision. From that data, researchers reconstructed the distribution of dark matter through a phenomenon called weak gravitational lensing, the subtle warping of background galaxies by intervening mass. Where the distortions are small, the mass is low. Where they vanish entirely, we find voids. DES revealed more than 1/400 of these hollows, some spanning hundreds of millions of light-years. But DES was only the beginning. In 2023, Euclid, the European Space Agency's dark energy mission, joined the search. Unlike ground-based surveys blurred by atmosphere, Euclid observes from space, combining visible and infrared cameras to chart the shapes and distances of 2 billion galaxies. Its goal to build the most detailed 3D map of cosmic structure ever made, one that extends 10 billion years into the past. By measuring how voids and filaments have evolved across time, Euclid will test whether general relativity itself still describes gravity on the larger scales. If the expansion or shape of these voids deviates from Einstein's predictions, we may be watching the signature of new physics. Perhaps dark energy is not constant, or gravity weakens differently than we expect. Meanwhile, on a lonely Chilean mountaintop, the Vera C. Rubin Observatory prepares to open its 8.4-meter eye to the entire southern sky. Its legacy survey of space and time LSST will image the heavens every few nights for a decade, capturing the dance of galaxies and supernovae with unprecedented continuity. Where Euclid provides sharpness, Rubin will provide motion, revealing how galaxies drift through the slow current of expansion and how voids inflate year by year. Over time, LSST will produce a living map of the cosmic web, a film rather than a photograph where nothingness itself moves. Even the James Webb Space Telescope, though not a survey instrument, contributes to this cartography of absence. Its deep field observations pierce the darkness to reveal faint background galaxies behind intervening voids, turning absence into contrast. By measuring how light from the earliest galaxies bends or fails to bend through these regions, Webb refines our knowledge of mass distribution in the universe's first billion years. Its infrared eyes can see the cosmic scaffolding before stars had even filled it. Together, these observatories transform the abstract concept of emptiness into something measurable, mappable, and alive. Their data flow into supercomputers that render the cosmic web as a three-dimensional lattice of filaments and hollows, an intricate honeycomb whose walls glow with galaxies, and whose interiors mark the frontier where gravity fades. These maps are not static. They record the universe at different epochs, showing how voids grow and merge, how the fabric stretches unevenly. For the first time, astronomers can test general relativity on scales of hundreds of millions of light-years. Einstein's equations predict exactly how fast voids should expand, how matter should flow along their edges, and how curvature should evolve as density declines. If the new surveys find discrepancies, if voids grow too quickly, or if light inside them bends too little, it could signal that our understanding of gravity is incomplete. In that sense, each 3D chart of emptiness becomes an experiment, a test of whether space-time behaves the same way in the voids as it does among the stars. Already early results hint at delicate tensions. DES observed slightly faster void expansion than the standard LCDM model predicts. Euclid's preliminary maps suggest subtle anisotropies directions, where the fabric seems to stretch more easily. Are these statistical flukes or whispers of modified gravity? The coming decade will decide. When Rubin's LSST begins its 10-year movie of the sky, Its billions of galaxies will anchor a network of cross-checks, comparing lensing redshift and flow. The very geometry of nothing will become the universe's most stringent test of Einstein's legacy. There is a strange beauty in this new science. For centuries, astronomy chased the light stars, nebulae, and galaxies blazing in the dark. Now it turns to the dark itself, to the spaces between where reality reveals its architecture by what it withholds. To map a void is to understand not just where galaxies are, but where they are not and why. In the end, these maps of nothing remind us that the universe's shape is defined by absence as much as by presence. We live inside one of those absences, a gentle hollow where gravity relaxes and time runs just a little faster. As our instruments trace its contours, we are in effect measuring our own address in the geometry of infinity. Next, we turn from the observation of voids to the meaning of them, how living in a universe that is mostly nothing changes the way we think about existence itself, matter as the exception, emptiness as the rule. When you pull back far enough past the galaxies, past the clusters, past even the walls that bind them together, the universe ceases to look like a collection of things and begins to resemble a pattern of absence. More than 90% of the cosmos is empty space, not pure vacuum but low-density regions so vast that entire superclusters could drift inside them without ever touching the walls. The galaxies we see, the filament nodes and bridges of the cosmic web, are merely the outlines of these voids, glowing seams around invisible bubbles. Matter doesn't fill the universe so much as trace its edges like frost forming along cracks in a window. This is the architecture of absence, a design built from subtraction. In the great cosmic surveys, when the data are rendered in 3 dimensions, the pattern takes on an eerie familiarity. The luminous filaments form a delicate mesh, threading through the darkness like neurons firing in a colossal brain. The voids, vast and silent, are the spaces between those thoughts, the pauses that give them meaning. Cosmologists sometimes describe this as a neural universe, an apt metaphor, networks of connection, surrounded by a darkness that both divides and unites. Another image, coral reefs seen from above. The bright ridges of galaxies form the reef's stony skeleton, while the voids are the lagoons between, teeming not with fish, but with potential the open sea where cosmic currents flow. Or picture the white foam of an ocean wave bursting outward in slow motion. The shining bubbles are the walls of matter. The darkness between them is the air itself, expanding, merging, dissolving. The universe frozen in its own surf. In this structure, the voids are not passive gaps. They are the framework's foundation, dictating where filaments grow, how clusters connect, even how light bends through the web. The gravitational potential of emptiness shapes the movement of everything around it. Galaxies gather where voids collide like debris piled between expanding soap bubbles. The result is a cosmic honeycomb, hexagonal in spirit, though irregular in form, a lattice of invisible rooms whose walls are built from the detritus of creation. Our own galaxy, the Milky Way, sits on one such wall, caught between neighbouring hollows like a bead of condensation between bubbles. On one side lies the KBC void, stretching nearly 2 billion light-years. On the other, the denser Virgo and Hydra Centaurus superclusters. We are literally living on the skin of nothingness, balanced at the interface between what is and what is not. Simulations capture this in hypnotic beauty. Run them forward through billions of years and the voids swell like lungs merging and reshaping. The filaments stretch thinner, the nodes tighten into small bright knots, and the whole structure begins to resemble a web of gossamer light suspended in black water. When cosmologists overlay these maps with the paths of galaxies, the pattern aligns with astonishing fidelity. The cosmic web is not chaos. It is a vast self-organizing geometry, born from gravity's simple law, acting on randomness. And yet the poetry of it remains in what's missing. The universe's elegance lies in restraint in how so little matter can define so much form. Less than 1 atom per cubic meter on average creates the pattern that fills the night sky. The galaxies are punctuation marks in an endless sentence written mostly in blank space. Philosophers once imagined the heavens as solid spheres. Now we know the opposite is true. The cosmos is more gap than structure, a cathedral of voids whose columns are light itself. The filaments are merely the mortar lines outlining the negative spaces that give the edifice its shape. If you could fly across billions of light years at once, compressing the universe into a single glance, you would see not a field of stars, but an intricate foam of emptiness glowing faintly, where galaxies trace its boundaries. You would see that existence itself is sculpted by what's missing, and that we, the dwellers of one faint strand, live along the edges of nothing. This perhaps is the universe's final humility. It doesn't need to be full to be whole. Its beauty resides in the rhythm between being and void in the luminous borders of emptiness. Next, we follow that realization to its human echo, how awareness of this cosmic architecture transforms our sense of meaning, solitude and belonging in a universe built mostly of silence. In the beginning, the universe was astonishingly smooth. Not perfectly perfection would have left it lifeless, but nearly so a mist of matter and light expanding together uniform to one part in 100,000. Those faint wrinkles seen today as the microwave ripples in the cosmic background radiation were the first whispers of structure. They were tiny variations in density regions slightly heavier or lighter than their surroundings, etched into the newborn cosmos less than 400,000 years after the Big Bang. Each of those ripples was a seed, a quantum fluctuation inflated to cosmic scale. During the brief explosive burst of cosmic inflation, microscopic variations in the quantum fields were stretched across light years, freezing into the plasma of the early universe as gentle compressions and rarefactions. When the universe cooled enough for light to travel freely, those ripples became visible as temperature variations on the CMB's surface, mere microkelvin differences subtle as breath on glass. 13.8 billion years later, those ghostly shadows have become the walls and voids of the modern cosmic web. Between those two moments lies the greatest act of natural amplification in existence, the transformation of a nearly featureless fog into a universe of galaxies, filaments and silence. Gravity was the amplifier. Once the primordial plasma cooled and recombined into neutral atoms, matter, decoupled from radiation, freeing it to move under its own weight. Wherever density was slightly higher than average, gravity began to tug more strongly, attracting nearby material and deepening the well. Wherever density was lower, matter drained away, leaving behind a swelling hollow. These minuscule contrasts, first measured by Kobe and later by WMAP and Planck, acted like blueprints for all future structure, gravity sculpting light's faint fingerprint into cosmic architecture. The process was slow, cumulative, and mercilessly patient. In the first 100 million years, the densest pockets condensed into dark matter, halos, invisible cocoons where baryonic gas could collect. These halos seeded the first stars and galaxies whose radiation reheated the surrounding space and added new turbulence to the cosmic medium. Meanwhile, the underdense regions, the primordial voids, expanded, pushing their edges together like bubbles in rising dough. Over billions of years, the contrast grew sharper. The rich got richer, the poor got emptier, a law of cosmic economics called gravitational instability. Every particle of matter deepened its own gravity well by attracting more neighbors. Every rarefied patch surrendered its material to the surrounding walls. The universe learned to exaggerate itself. What had been a gentle variation of one part in 100,000 became, after eons of reinforcement, a structure of one part in one full versus empty wall versus void. The mathematics of this transformation lives in the equations of linear and nonlinear growth. In the early universe, when fluctuations were small, density contrast. D grew roughly in proportion to the scale factor of T, AT. But as overdensities became stronger, the process accelerated, entering the nonlinear regime where collapse into galaxies and clusters occurred. The voids conversely expanded faster than the background universe their interiors nearly evacuated. By redshift 0, our epoch, the contrast between wall and void is extreme, a difference not of fractions but of magnitudes. Simulations visualize this evolution like time-lapse art. Start with a uniform grey fog slightly mottled like noise on an old television screen. Run gravity forward and the speckles swell and merge. Filaments stretch, voids bloom. By halfway through the simulation, the pattern already resembles lace-dark gaps threaded by shining veins. Let it run to the present and the cosmic web appears glowing golden against darkness, all of it born from fluctuations so small they could once fit inside the whisper of a photon's warmth. The story written in those ripples is the story of balance. Too much smoothness and nothing ever forms. No galaxies, no stars, no observers. Too much irregularity and the universe collapses into chaos long before life can begin. The actual universe threaded the needle. Its early contrasts were exactly strong enough to yield structure exactly weak enough to last. The CMB's one part in 100 order pattern wasn't a flaw, it was a design threshold, a cosmic seed budget calculated by nature itself, Even now, the connection remains visible. When we map the large-scale structure of galaxies and compare it to the pattern of CMB fluctuations, they align in haunting fidelity. The hot and cold spots of the early universe correspond to the walls and voids we see today. The same fluctuations that rippled through the infant plasma now define the scaffolding of everything that exists. We are literally the condensed memory of light. Think of it as a great metamorphosis, the smooth shell of the cosmic egg cracking into filaments, light's small unevenness turning into galaxies, the faintest statistical whisper growing into the thunder of structure. From smoothness came the web, from uniformity complexity. The voids we live in are not accidents, but legacies, the natural expansion of the universe's original low points. They are the echo of those ancient ripples still expanding, still shaping the pace of cosmic time. Every atom of us was once part of that first faint pattern. The oxygen we breathe, the iron in our blood, the stars that light the sky, all are frozen. Amplifications of a fluctuation 1/10,000th, the width of a hair stretched across the early universe and allowed to mature under gravity's patient hand. In the next part, we return from this long evolution to the present to contemplate what it means that the universe has spent nearly 14 billion years sculpting complexity from smoothness, and what happens now that the sculptor's hands are letting go. To be here inside this vast and silent hollow is to occupy one of the rarest places in the known universe. Not rare in beauty, for every region of the cosmos has its grace, but rare in statistics, the likelihood of a void like ours of this scale and depth arising exactly where we happen to live is less than 1 in a million. The KBC void, nearly 2 billion light-years wide and about 20% below the average cosmic density, is not something the standard cosmological model predicts often. Simulations of the LCDM universe generate millions of regions. Only a handful resemble this. We exist, it seems, in an improbable bubble of emptiness and anomaly within an otherwise orderly web. Astronomers Keenan, Barger and Cowie, who first quantified it in 2013, were careful to phrase their discovery in neutral tones, a local underdensity consistent with large-scale structure. Yet beneath that phrasing lies astonishment. When later surveys confirmed the pattern, fewer galaxies nearby, a slightly elevated local expansion rate, it began to look as though our cosmic address had been chosen from the tail of a statistical distribution, a 1 in a million draw. The universe, as usual, had made room for both order and exception. And perhaps that is the deeper echo, one that resonates beyond equations. Humanity has always found itself perched in unlikely niches suspended between extremes. We live on a planet balanced just far enough from its star for water to remain liquid, in a solar system stable enough to survive billions of years, in a galaxy whose spiral arms move neither too fast nor too slow for life to endure. Now we learn that even on the grandest scale, the architecture of the cosmos itself, we inhabit an anomaly, a gently underdense cocoon, where expansion runs slightly faster, time ticks slightly freer, and gravity's voice is softer. It is tempting to read meaning into that rarity, to imagine purpose in probability, but perhaps the more elegant truth is that exception is the rule of consciousness. Life by its nature arises where the improbable lingers. The same delicate asymmetry that allowed matter to outnumber antimatter after the Big Bang, the 1 in a billion excess that made galaxies possible, also made us. Against that cosmic backdrop, a 1 in a million void feels almost ordinary. Still, there is poetry in the alignment. From this position inside the KBC void, we can see farther and more clearly than we might from denser realms. The low foreground dust, the reduced gravitational lensing, and the slightly faster local clock all grant us an unusually transparent window onto the universe. We are quite literally in a privileged observatory carved by emptiness itself, a cosmic balcony from which we watch the whole. It is easy to forget how many layers of improbability rest beneath every human gaze at the night sky. Each photon that reaches our eyes has travelled for billions of years through this underdense corridor, dodging clusters and filaments, arriving unscattered to tell its story. The darkness we see between stars is not a void in the poetic sense, it is the void, the very structure of the region that shelters us. Statistically, we should not be here, and yet we are. Perhaps that is the recurring pattern of existence. The cosmos generates trillions of possibilities, and meaning unfolds in the outliers. Every improbable island Earth consciousness, this luminous cavity of space, is part of a larger rhythm in which rarity becomes perspective. In an infinite universe, there must be regions richer, emptier, brighter, darker. Yet it is in this unassuming corner, inside a faint hollow of matter, that the universe has evolved eyes capable of seeing itself. The very fact that we can measure the improbability of our location makes that location special beyond all measure. The KBC void is not merely a curiosity of astrophysics. It is a mirror held up to our condition. We are always the exception, observing the rule, the observers inside the hollow wondering how the hollow came to be. And perhaps that is the true symmetry. The universe in its immensity needs a few improbable places so that it can be known at all. In the end, the odds are beside the point. What matters is that from within this rarest of regions, amid 90% nothingness, a thin strand of matter learned to ask why, and to listen in the quiet between galaxies for the echo of its own astonishment. Inside the voids, the universe moves at half speed. Galaxies drift through vast silence, their motions unhurried, their histories unscarred by collision or conquest. To live here among the emptiest regions of space is to experience cosmic solitude in its purest form. These are the dwarf galaxies of the voids, tiny islands of light adrift in oceans of darkness. Unlike their bustling cousins in clusters and filaments, they evolve in near isolation. They have few neighbours, fewer mergers, and long uninterrupted lives. Their stars are older, their gas cleaner, their shapes simpler. In every sense, they are galaxies in slow motion. When astronomers first surveyed these regions with the Sloan Digital Sky Survey, and later with radio telescopes like Alfalfa at Arecibo, they found a paradox. The voids were not completely empty. Thousands of faint blue, low-surface brightness galaxies dotted their interiors, but they were markedly different. They contained less stellar mass, weaker central bulges, and virtually no massive ellipticals. Most were irregular or disc-shaped fragile things untouched by violence. Why? Because structure here grows slowly. In the early universe, density fluctuations within voids were too small to collapse efficiently. Gravity starved of mass took billions of years to gather enough material for even modest galaxies. By the time the first stars lit up in the filaments, void galaxies were still assembling their halos. Their chemical fingerprints reflect this delay. They are metal poor containing gas that has undergone fewer cycles of stellar birth and death. Each new star forms from cleaner material unpolluted by heavy elements. Observers describe them as primordial laboratories, miniature versions of the young cosmos still playing out ancient physics. These dwarfs also age differently. In clusters, galaxies grow by collision. They still gas-ignite starbursts and then quench as interactions strip their fuel. In voids, there are no close encounters to trigger drama. Star formation proceeds slowly, sustained by gentle accretion from the intergalactic medium. Their disks remain thin, their spiral arms loose and delicate, their histories written in lowercase. Radio observations reveal another distinction. The gas halos around void galaxies extend far beyond their stellar bodies, sometimes 5 or 10 times larger than the visible light would suggest. This hydrogen reservoir serves as a time capsule preserving conditions akin to those of the early universe, where cluster galaxies have been sculpted by pressure, wind, and gravity. These isolated dwarfs float untouched, their evolution guided only by the faint push of cosmic expansion. The result is an aesthetic of simplicity. Photographs from telescopes like Hubble and JWST show pale, diffuse disks peppered with small blue star clusters, drifting without companions. Some exhibit faint gaseous tails, signatures of slow, gravitational tides from distant neighbours, but most simply shine against blackness, serene and self-contained. In their stillness, they embody what cosmologists call environmental quiescence evolution, driven by internal processes, not external interference. There is something almost monastic about them. While the galaxies and crowded clusters burn through their fuel and merge into massive ellipticals, the void dwarfs linger content in their isolation. They will likely continue forming stars for trillions of years, long after the cosmic web has thinned beyond recognition. In them, the universe keeps a quieter tempo, a whispered coda to the symphony of structure. And yet these lonely systems are not irrelevant. They are crucial tests of cosmological theory. Their abundance, metallicity, and rotation curves probe how dark matter behaves in low-density environments. Some models predict far more void dwarfs than we observe, a discrepancy known as the void phenomenon, a small but persistent puzzle hinting that our simulations may still underestimate how feedback and cosmic flows shape the smallest galaxies. In that sense, even the universe's loneliest inhabitants keep teaching us how the whole evolves. For the human mind, there's an uncanny resonance here. In the isolation of these galaxies, we glimpse a reflection of ourselves, tiny civilizations orbiting through silence, growing in slow motion, preserving ancient memories of creation. Just as void galaxies remain chemically pure because nothing has disturbed them, perhaps thought too deepens in quiet environments where the noise of collisions fades and time can stretch. If the filaments are the universe's cities, the voids are its monasteries, spiritual sanctuaries of matter where simplicity endures and chaos never quite arrives. From here we can imagine the final epochs, when such galaxies will be the last lights burning in a universe grown thin, their gentle rhythms continuing long after gravity itself has gone still. Next, we turn toward that future. What happens when the web of matter ceases to connect? When even these isolated galaxies drift beyond one another's reach, and the universe breathes its final quiet expansion. There comes a moment after the maps are drawn and the equations balance when cosmology crosses quietly into philosophy. We begin by studying emptiness, by counting galaxies, measuring density, quantifying voids, and end by confronting a truth so simple that language barely holds it. Nothingness is not the opposite of something, it is its foundation. Modern science, with all its instruments and precision, has confirmed what ancient mystics intuited in silence. Emptiness is the architecture within which being unfolds. The universe is not a stage filled with matter, but a vast dynamic emptiness that lends matter its context, its motion, its meaning. Einstein himself hinted at this when he spoke of space-time as a fabric. Remove all stars and atoms, and the fabric remains not as a backdrop but as an entity that curves, flexes, and evolves. The voids are the purest form of that fabric, nearly free of matter, revealing what the universe is made of when it is made of almost nothing. Their expansion, their softness, their quiet acceleration, all are expressions of the fundamental geometry that underlies existence. In that sense, the cosmic void is not absence at all, it is structure in its most essential form. The walls and filaments we see are simply the lines of stress where nothingness has folded upon itself the wrinkles of an invisible medium. Matter does not define the void defines matter, outlining it, giving it contrast. As the poet of relativity Hermann Weyl once wrote, the world is not filled with things, but with relations. Across cultures and millennia, human thought has circled this realization. In Taoist philosophy, the usefulness of the bowl lies in its emptiness. In Buddhist sutras, the essence of reality is shunyata, emptiness that is not void but potential. In Western mysticism, the apophatic God is defined not by presence but by infinite space. Science through its telescopes has arrived at the same threshold, the recognition that the universe's form arises from what it lacks. When we map the voids, we are mapping the scaffolding of possibility itself. The hollows between galaxies are like pauses between notes in a melody. Without them, there would be no rhythm, no song. Light needs darkness to reveal its trajectory. Gravity needs emptiness to express curvature. Thought needs silence to take shape. Inside the KBC void, the analogy becomes literal. We live in a region where the universe relaxes into its own breath, where expansion outpaces density, where matter is thin enough for the underlying fabric to show through. It is as if creation gave itself a clearing, a moment of stillness in which to perceive itself. That is the miracle of our coordinates. We dwell in one of the rare places where the universe can look inward and see its own design. There is also a humility in this realization. For centuries, humanity has searched for significance by placing itself at centers geographical solar galactic. Now we discover we live in a void, a low-density anomaly, a hollow between walls of galaxies. But perhaps this is not demotion. Perhaps it is grace. The best place from which to contemplate the whole is not the crowded hub, but the quiet edge. From emptiness, the shape of everything becomes clear. In this convergence of cosmology and contemplation, nothing ceases to be a deficit. It becomes the creative condition, the fertile silence that allows structure, life, and meaning to arise. The cosmic web is not a battle between being and void, it is their collaboration. Space itself, elastic, self-sustaining, generous, is the ultimate artist sculpting galaxies out of gradients, stars out of whispers, consciousness out of contrast. So when you stare into the dark between stars, you are not looking into nothingness. You are looking into the ground of everything, a living emptiness, whose stillness holds the rhythm of all motion, whose silence contains the potential for all sound. And in that recognition, science, and spirituality touch. One names it space-time, the other calls it the void, the Tao, the uncarved block. Both point to the same mystery that the universe at its heart is not a collection of things, but an active relationship, a harmony woven from absence and presence. We began by measuring a hollow. We end by realizing that the hollow measures us, that our minds too are formed by spaces between thoughts, our lives by pauses between events, our meaning by the contrast of being and non-being. The truth of nothingness is not despair, but design. It tells us that to exist is to participate in the dance of emptiness, to shine briefly against the background of infinity, to move within the silence that gives all light its shape. Next, in the final part, we return to that silence, seeing the universe not as a puzzle to solve, but as a lullaby to rest within a cosmos of breath, balance, and belonging. The universe measures itself through us. Every telescope, every detector, every spectral line is a mirror held up to the cosmos, light reflecting light. Yet the act of measurement is never neutral. It bends with perspective shaped by where we stand and how our instruments translate the language of space-time. To know how fast the universe expands, we must therefore use many mirrors, each polished to a different truth, each correcting the distortions of the others. The story returns full circle to the Hubble constant, the cosmic yardstick of expansion. We've seen how local measurements built on Cepheid stars and supernovae can be biased by our location inside a void, our moving laboratory adrift in low density. To see beyond that bias, astronomers have turned to other rulers, yardsticks born not of brightness, but of geometry, not of proximity, but of physics written into the universe itself. One such ruler is gravitational redshift, the change in light's frequency as it escapes gravity's pull. Every photon climbing out of a potential well loses energy, its wavelength stretched just as the universe stretches space. On galactic scales, this redshift encodes both motion and curvature. When light from a distant galaxy arrives slightly redder than predicted by pure expansion, part of that signal comes from the galaxy's own gravity. Part comes from the large-scale structure between us and it. By disentangling these effects, astronomers can infer how deep the gravitational landscape truly is, how much mass lies hidden along the way. In practice, surveys like DESI and Euclid measure this effect statistically across millions of galaxies. Each individual redshift is a small clue. Together they trace the cosmic potential field like contours on a map. The patterns reveal how matter clumps and how quickly structures grow, direct tests of general relativity on scales of hundreds of millions of light years. And because gravity's imprint is universal, it is less susceptible to the local peculiarities that trouble our neighborhood measurements. A second, even more powerful ruler arises from the early universe itself, the baryon acoustic oscillations, or BAO. Long before stars formed, the cosmos was a hot plasma of photons, and baryons, particles of light and matter, locked together, vibrating like sound waves in a dense fog. These oscillations traveled outward from every dense region, leaving behind a faint preferred separation scale, about 500 million light-years between clusters of galaxies. When the universe cooled and atoms formed, the waves froze, imprinting that scale onto the distribution of matter forever. Today, when we map galaxies in 3 dimensions, we can still see that subtle rhythm, a slight excess of pairs separated by the BAO distance. It's a cosmic yardstick independent of stars dust or local voids, calibrated by the physics of the primordial plasma itself. Measuring how that scale appears, stretched or compressed at different redshifts, tells us how much the universe has expanded since those waves froze. It is in essence the sound of creation turned into geometry. The beauty of BAO lies in its indifference to local conditions. While supernovae and Cepheids measure expansion nearby within a few hundred million light-years, BAO spans billions. It samples so vast a volume that no single void can bias it. When astronomers plot its results, they find a value of the Hubble constant close to the Planck prediction, around 67 km to MPC, confirming that on the larger scales, the universe's tempo is calmer, slower, more even than our local reading suggests. But even these cosmic yardsticks are not enough alone. Each method measures a different aspect of expansion, brightness, geometry, velocity, clustering. Together they weave a tapestry of cross-checks that define modern cosmology's strength. The cosmic microwave background gives the baseline tempo. Supernovae provide the present beat. Gravitational lensing measures how the fabric flexes between them. Baryon acoustic oscillations set the scale. Time delays and quasars add the rhythm of cosmic clocks. It is by comparing these many rhythms that astronomers can distinguish local weather from global climate perspective from truth. And yet, even with these tools, a subtle mirroring remains. The light we measure has passed through everything that defines our vantage, our galaxy, our local void, our motion through space. Every correction we apply is a recognition that we too are part of the system. The act of observing folds the observer into the observation. We measure the universe not from outside, but from within its curvature through its own mirror. In this sense, the quest to refine the Hubble constant is not just about precision, it is about understanding ourselves as instruments of the cosmos. The photons that left a galaxy billions of years ago now fall into our telescopes slowed or sped by every contour of space-time between. Their redshift encodes the total history of expansion and gravity's pull. When we decode that message, we are reading the autobiography of the universe, one written in light, annotated by emptiness and interpreted by minds made from stardust. Multiple yardsticks are our way of humility. No single measure can claim the final word because every measure is shaped by context. But when the mirrors align, when Cepheids, BAO lensing, and the cosmic microwave background all reflect the same truth, we glimpse something purer, the universe revealing itself through consistency, balance, and self-symmetry. In that reflection, cosmology becomes both science and mirror meditation. Each distance we chart, each redshift we decode brings us closer to recognizing that our understanding of space and time is itself a product of the space and time we inhabit. The universe measures us as surely as we measure it. Next, in the closing part, we bring all these reflections together, the science and the silence, the structure and the void, to ask what it means to belong to a cosmos that is still expanding, still learning, and still awake within itself. The deeper we measure time, the more it refuses to sit still. The universe, like a patient in its own examination, gives two conflicting ages depending on which instrument you use. The Planck satellite, reading the afterglow of the Big Bang, says the cosmos is 13.8 billion years old. The local measurements derived from faster expansion inside our underdense region shorten that history to around 12.7 billion years. And then, as if to tease both, a few ancient stars seem older still. The most famous of them, HD Wars or Fullsonskutu H3, shines just 190 light-years away in Libra. Astronomers call it the Methuselah star, a population 2 subgiant of almost pure hydrogen and helium, one of the firstborns of the Milky Way. Its light carries the signature of ancient nucleosynthesis with barely any metals. Using stellar evolution models, researchers once estimated its age at 14.5 plus spawns, 0.8 billion years older, within error bars than the universe itself. Even after refinements, the best estimates still hover around 13.5 within a cosmic whisker of contradiction. If the local expansion rate really is higher, the paradox deepens. A faster Hubble constant compresses cosmic chronology, the same redshift translates to less time since the Big Bang. In the local frame, the cosmos looks younger, yet its oldest stars keep their slow-burning certainties. Time itself seems to stretch and shrink depending on where we measure it, as if the universe were composed of overlapping timelines, each valid, none entirely reconciled. How can a star outlive its universe? There are several possible answers, each a glimpse into physics still unsettled. One explanation points to our cosmic neighborhood, the void we inhabit. In an underdense region, gravitational potential is shallower and time flows faster. Observers inside a void might perceive cosmic events as happening sooner, effectively aging faster relative to the global average. This void time dilation could add hundreds of millions of apparent years to local chronometers. From the outside, nothing paradoxical occurs. It's simply relativity at work. From within, it feels like the universe itself is older than its clock allows. A second possibility invokes evolving dark energy. The LCDM model assumes a constant cosmological, constant dark energy with fixed density and unchanging pressure. But if dark energy has evolved, increasing in influence only recently, then early expansion would have been slower, giving stars more time to form before the universe reached its current size. A dynamic dark energy field, sometimes called quintessence, could stretch the timeline back toward harmony, aging the cosmos to fit its oldest lights. A third possibility is more mundane yet equally profound calibration error. The ages of stars depend on models of nuclear fusion opacity and element diffusion. Change any parameter, the abundance of oxygen, the treatment of convection, the precise rate of proton-proton reactions, and the stellar clock shifts by hundreds of millions of years. In recent years, improved parallax data from Gaia and better reaction rates have trimmed Methuselah's age down to 0.4 billion years, comfortably within the Planck value. The crisis may be less a violation of physics than a reminder of how delicate the bridge between theory and observation really is. Still, the tension remains more than numerical, it's philosophical. To find a star whose age once seemed to exceed that of the cosmos is to confront the fallibility of our assumptions about time itself. It exposes the layered nature of cosmological truths. The universe has many clocks, stellar, galactic, gravitational, and they do not all agree. On some level, the paradox is inevitable. Cosmic time is not a single universal heartbeat. It is a collection of local tempos stitched together by relativity. Matter slows time, voids quicken it, and expansion stretches it everywhere. The age of the universe, like its size, depends on the vantage from which you measure. And yet there is something quietly reassuring in this. The Methuselah star does not actually disprove cosmology, it illuminates it. Its near impossible age reminds us that the universe's history is not a fixed ledger, but a conversation between matter and light model, and measurement the near and the far. As our instruments sharpen and our models evolve, those numbers will converge again, just as they have before each generation of telescopes, bringing the cosmos back into tentative alignment. For now, the paradox remains a kind of cosmic quan. How can a star be older than everything? Perhaps because everything includes the space that makes aging possible, and that space flows differently in different places. In the end, the age crisis is not an embarrassment, but an invitation. It tells us that our understanding of time, like the universe itself, is still expanding. Next, we conclude our long journey through the hollows, the final meditation on what it means to inhabit a cosmos built of impermanence, stitched together by light and held open by nothingness. In the deep fields of James Webb, the early universe does not tiptoe into existence. It arrives already crowded with bright, heavy systems where theory expected only flickers. Galaxies with billions of suns worth of stars blaze at redshifts beyond 12, meaning they shone when the universe was less than 350 million years old. Some show smooth stellar disks, rich reservoirs of gas and spectral lines that hint at surprisingly mature chemistry. The first reaction was wonder. The second was vertigo. If such mass and order existed so soon, then either the cosmos learned to build fast or our clocks for reading its timeline are off. Astronomers speak softly about broken clocks, but the metaphor fits. Our chronometer's stellar population models, halo growth rates, the expansion history that converts redshift to age, were calibrated for a universe that assembles on a measured schedule. JWST looks back and finds early giant systems too luminous, too massive, or too organized for the allotted time. To reconcile the picture, we can adjust three dials: how fast matter collapses, how efficiently it turns into stars, and how we interpret the light. Each solution changes the tempo of cosmic history in a different way. First, faster assembly. In the LCDM framework, dark matter halos grow by accreting smaller halos along cold filamentary streams. That picture can in principle ramp quickly, especially in rare peaks of the primordial density field. If the earliest overdensities were a touch more extreme than average in the regions JWST has sampled, they could host halos with enough gravity to pull in gas at furious rates. The Webb would feed them from multiple directions, minimizing angular momentum bottlenecks, letting disks settle quickly. Star formation could ignite in bursty episodes, briefly pushing galaxies to brilliant luminosities that make them look older than they are. In this scenario, the universe isn't cheating time, it's spending it wildly in a few privileged places. Second, higher efficiency. The ratio of gas inflow to starlight might be skewed in the primordial era. If the initial mass function IMF was top-heavy, favoring massive short-lived stars, then a young galaxy could appear both bright and mature, because massive stars flood the spectrum with ionizing photons and heavy elements quickly. Likewise, weaker stellar feedback in metal-poor gas might allow more material to collapse before supernova winds blow it out. Even small, dense clumps could convert a startling fraction of gas into stars in a few tens of millions of years, inflating the observed stellar masses and metallicities. The clock isn't broken here. Its hands move faster because the mechanism is more efficient at every tick. Third interpretation, our favorite trap. Inferring mass and age from starlight is an art of assumptions, star formation history's dust content, metallicity, nebular emission, and the exact redshift. At ZRS-12, photometric redshifts depend on a handful of filters. Strong nebular lines can masquerade as older stellar populations. Dust can redden the spectrum and trick models into assigning too much mass. Lensing can magnify faint systems so they seem inherently larger. Gebusti spectroscopy has already confirmed some astonishingly early objects, but for others the uncertainties remain wide. Tune the models, allow for bursty star formation, let emission lines carry more of the flux, adopt slightly different priors, and a massive old system can become a young upstart mid-flare. In this reading the clock is fine, we simply misread the face, and yet even after careful recalibration something stubborn lingers. A subset of early galaxies remain too luminous and too numerous to sit comfortably inside the old forecasts. Their presence nudges us to revisit the expansion history itself. If local measurements of the Hubble constant are biased high by our underdense region, then our conversion from redshift to cosmic age at early times might slide subtly, but enough to matter. A universe that expanded a bit more slowly in its first few 100 million years would grant galaxies extra time to assemble before we catch their light. That is one flavour of the early dark energy idea, a transient component that tweaks the growth of structure without overturning the late-time acceleration we see today. Not a new universe, just a universe that front-loaded opportunity. There is also the possibility that the initial conditions carried slightly more small-scale power than Planck's best-fit parameters suggest. A gentle boost to the amplitude of tiny primordial ripples still consistent with the CMB within error bars would seed more rapid early collapse, producing more halos capable of feeding JWST's prodigies. Even a few % change at the beginning compounds into dramatic head starts by Z10. Whatever the mix of causes, the implications are profound. If early star formation was faster and more efficient, then the reionization of the universe, the moment when ultraviolet light from newborn stars stripped electrons from hydrogen, may have proceeded more swiftly, with bright pockets appearing like lanterns in a fog. The chemical timeline shifts. 2 supernovae would seed heavy elements earlier, enabling the first dust grains to cool gas and accelerate the next wave of stars. Black holes born from the first giants could fatten quickly, explaining the quasar beacons seen when the universe was still an infant. One adjustment at dawn cascades through every rung of the ladder, and yet there is comfort in the discipline with which cosmology tests itself. JWST does not overthrow, it interrogates. Its early giant discoveries force cross-examinations with baryon acoustic oscillations, weak lensing maps, and the cosmic microwave background, the independent clocks and rulers we use to keep perspective honest. If they converge on a single story, we will know the fix is subtle. A revised IMF here, a feedback recipe there, an early time tweak to expansion. If they diverge, we will be staring at the threshold of new physics, gravity, or dark energy behaving differently in the first act than in the third. For now, the most human response is wonder. The sky we thought we knew as a quiet nursery turns out to have been a workshop banging out bright organized systems at a rate that feels beautifully improbable. The metaphor of broken clocks softens under this light. Perhaps the clocks weren't broken. Perhaps they were set to local time while JWST reported cosmic time, or vice versa. Perhaps the universe keeps multiple rhythms at once, and our task is to score the symphony. In the calm cadence of science for sleep, the message is gentle. The early universe was more alive than we imagined. Its hands moving quickly, its builders unhurried by our expectations. We will refine the models, retune the dials, and adjust the tempo. But the melody, gravity collecting, gas cooling stars igniting remains the same. The first giants arrived early not to shame our clocks, but to remind us that time in cosmology is a conversation measured by many instruments, heard from many seats in the hall. Close your eyes and picture a dark stage, a few lanterns igniting far sooner than the script allowed, casting longer shadows than our equations predicted. We adjust our watch smile at the surprise and listen more closely. The play goes on, and we are awake for it. In the beginning, cosmologists thought the vacuum was simple, a constant, a quiet pressure woven evenly through all of space. Einstein called it the cosmological constant L, an unchanging energy density that pushes outward as gravity pulls in. It was elegant, stable, and convenient until the universe began to behave like something more alive. Now the idea of a variable vacuum, a living form of dark energy, is emerging from both theory and observation. Instead of being fixed, dark energy might evolve across time, and even vary across space, its strength shaped by environment. The name for this restless idea is quintessence, a nod to Aristotle's fifth element, the invisible essence thought to fill the heavens. In modern cosmology, it describes a dynamic field, like a cosmic weather pattern, whose pressure and density shift as the universe expands. In equations, quintessence replaces L with a scalar field, a kind of potential energy that can roll, oscillate, or cluster ever so slightly. Where the field is higher, expansion accelerates more strongly. Where it dips, gravity gains a momentary advantage. The result is a universe not driven by a single constant pressure, but by a changing one of vacuum that breathes. And perhaps as new observations hint that breathing is not uniform. Inside the vast cosmic voids where matter is scarce and curvature shallow, the scalar field could stretch more freely like a fabric relieved of tension. Some models predict that dark energy's local density might actually be stronger in these underdense regions, accelerating expansion faster there than in crowded cosmic neighborhoods. The effect would be tiny, but cumulative voids expanding a bit more vigorously, walls tightening a bit more slowly, the global average emerging as a weighted blend of faster and slower patches. In that sense, dark energy becomes not a constant backdrop, but a participant in the structure of space of variable vacuum adapting to its environment. The idea is both mathematically plausible and aesthetically disquieting. It would mean that the fundamental energy of the universe, the thing driving its acceleration, is itself inhomogeneous. The vacuum would have texture. To visualize this, imagine a landscape of low hills and gentle valleys stretching across the cosmos. In the dense filaments and clusters where gravity's grip is firm, the quintessence field lies compressed in the valleys subdued by mass. Inside the voids, the field rises to the hilltops, free to roll with higher potential energy. The result is a universe where the rate of expansion varies subtly from place to place, guided by the invisible topography of this field. Such a pattern could help explain why our local region, the KBC void, appears to expand slightly faster than the cosmic mean. The local underdensity might not only weaken gravity, but also amplify dark energy's influence, turning our surroundings into a patch of overactive vacuum. In this view, the Hubble tension is not merely an observational bias, it's a clue that dark energy itself responds to its surroundings. The physics of quintessence offers many flavors. If the field's pressure changes gently with time, its equation of state parameter, UIPRW, PBN, how P, pressure over density, would deviate from the L value of 1, perhaps hovering around 0.95 or oscillating with cosmic cycles. If it interacts weakly with matter, its influence could cluster slightly, imprinting small deviations in the expansion rates of voids versus filaments. Some models even let quintessence exchange energy with dark matter, leading to feedback loops that subtly alter how structures form. Observationally, missions like Euclid, the Vera Rubin Observatory, and the Nancy Grace Roman Space Telescope are designed to catch these whispers of variability. By measuring how voids grow and how distant supernovae fade, they can test whether dark energy's push changes over time or with environment. A constant L leaves one fingerprint. A living field leaves another. Even a 1% deviation could signal that the vacuum is not an inert backdrop, but a dynamic actor in the cosmic story. Philosophically, the notion is hauntingly familiar. Ancient thinkers imagined the ether as a medium that filled all space, carrying both light and motion. Quintessence revives that intuition in a modern key, the vacuum as a living field, flexible and responsive, its properties tuned by the very emptiness it inhabits. The deepest voids, once thought to be the universe's blank spaces, may instead be its purest laboratories, where the nature of the vacuum reveals itself most clearly. If true, this would blur the last distinction between matter and nothing. The void would no longer be the absence of energy, but its most vivid expression, a realm where the universe's latent potential surges unopposed. The darker the region, the more freely the field can flow, and perhaps that is fitting. For billions of years, the cosmos has been teaching us that emptiness is never empty. First we learned that vacuum contains fields and particles, then that those fields drive expansion. Now we suspect that the expansion itself may differ from void to void. The universe, like a vast organism, adjusts its pulse depending on where it is thin and where it is thick. In that breathing, we can almost sense intelligence, not consciousness, but coherence. A variable vacuum would mean that the cosmos regulates its own tempo just as lungs adjust their rhythm to the body's needs. Inside the densest clusters, gravity binds. Inside the deepest voids, the vacuum exhales. Next, we explore how this living vacuum shapes the ultimate future, whether a dynamic dark energy means endless acceleration, a gentle slowdown, or something stranger, still a universe whose expansion like breath one day reverses. Imagine space itself as a lung and invisible organ spanning billions of light years, inhaling and exhaling, with a rhythm set by the balance between gravity and the vacuum. In the crowded filaments of galaxies, that breath is shallow and slow, checked by the weight of matter. But in the vast hollows between where galaxies thin and gravity weakens, the breath quickens. The fabric of space-time expands more freely there, as if the universe breathes faster wherever it is emptier. This vision is not just poetry. It is the hypothesis that missions like Euclid and the Dark Energy Survey Ds are now testing, with unprecedented precision. Does dark energy, the force driving cosmic acceleration, remain constant everywhere, or does it vary, exhaling most strongly inside the voids? To answer, astronomers are turning the cosmos into a laboratory of natural experiments. Each void and filament becomes a data point in a grand comparison between where space stretches easily and where it resists. The key tools are weak gravitational lensing and baryon-acoustic oscillations. BAO2, complementary ways of measuring how the universe breathes. Weak lensing works like this: as light from distant galaxies travels through space, it bends slightly around any mass it encounters. In dense regions, this bending is strong and organized, warping the shapes of background galaxies into subtle arcs. In voids, the effect flips sign, light rays diverge, stretching images outward instead of inward. By statistically mapping these shape distortions across millions of galaxies, DES has built a topographic map of cosmic curvature, revealing where space is taut and where it slackens. If dark energy is stronger in emptier regions, then the lensing signal across voids should be weaker than gravity alone predicts. Space there would be expanding faster than expected, diluting the mass and flattening its imprint on background light. Early D's results already hint at this. Voids appear slightly puffier than simulations based on a perfectly constant L would allow. Euclid, with its billion galaxy survey and sharper resolution from orbit, will take this test to the next scale, measuring how the divergence of light through voids evolves over time, watching the universe's lungs inflate in slow motion. This second test, the BSO shift, reads the same expansion in a different language. Recall that baryon acoustic oscillations left a preferred separation of roughly 500 million light-years between galaxy clusters, a frozen echo of sound waves from the early universe. As the cosmos expands, that ruler stretches. If dark energy's strength differs between regions, the stretching will not be uniform. Void dominated directions will show slightly larger bow scales, denser ones slightly smaller. By comparing these patterns in different environments, Euclid's 3D galaxy map will reveal whether the universe's expansion rate depends on how much matter lies nearby. Together, these measurements form the most delicate stethoscope ever placed on the cosmos. The breath of dark energy, if it exists, will reveal itself as subtle deviations, a few percent difference in the growth rate of structure, a gentle drift in the apparent size of the Bow ruler, a faint asymmetry in the shear of background galaxies. Each signature is like hearing the lungs of space take a deeper inhale where gravity's weight is gone. To visualize it, imagine watching the universe through time-lapse photography. The filaments dense and slow expand, little their walls thickening only slightly over billions of years. The voids by contrast bloom like soap bubbles, their boundaries glowing with galaxies that drift apart like pollen on the wind. If you could color the vacuum by the rate of its expansion, the map would pulse deep blues in clusters where dark energy is muted, warm golds in voids where it surges. Space would appear alive, breathing through gradients of emptiness and mass. In this picture, the variable vacuum becomes a dynamic participant in cosmic structure, not a static background constant. The universe's acceleration is no longer uniform but textured, its rhythm, modulated by where matter gathers and where it has fled. The large-scale structure we see, the cosmic web, would then be more than a relic of gravity's past. It would be the living record of the vacuum's present, tracing how each region of space responds to the same underlying energy in its own tempo. Dees has already provided the first inhalations of this cosmic lung. Euclid will capture the exhale. Together they may tell us whether the universe breathes with one steady pulse or with many. If the latter proves true, if dark energy is truly variable, then the voids around us are not silent emptiness, but the beating chambers of the cosmos itself, where the fabric of space expands most freely, carrying the rhythm of creation forward with every breath. Next, we explore what that rhythm may lead to, how a variable vacuum might shape the long future of the cosmos, whether the breath of dark energy grows shallower, steadier, or endless. Inside the cosmic voids, gravity does something profoundly counterintuitive. It doesn't pull things inward, it lets them go. Here in the loneliest expanses of the universe, the familiar direction of gravity is reversed by context. There is no central mass for galaxies to fall toward, only a vast underdensity surrounded by denser walls of matter. The void's geometry itself dictates the flow gravity always points from regions of low density toward regions of higher density. Inside a void, that means the net gravitational pull on any galaxy aims outward toward the encircling filaments. This phenomenon, called gravitational outflow, sounds like magic, but is simply mass balance playing out across billions of light years. Every patch of space tugs on every other. In a dense cluster, the tugs combine inward. In a void, most of the tugs come from the outside. The result is an effective repulsion, not because gravity pushes, but because there's more gravity in every direction except the one behind you. Simulations capture this beautifully. Cosmologists use them to watch the cosmic web grow from faint initial ripples into its present sponge-like form. The Millennium Illustrious TNG and Eagle projects each evolved billions of virtual particles, dark matter and gas under Einstein's equations for expansion and Newton's for attraction. What emerged over billions of simulated years were immense cavities, tens to hundreds of megaparsecs across, ringed by bright filaments of galaxies. Inside these hollows, matter streams away from the center, tracing gentle arcs toward the surrounding walls. Each simulation shows the same dance, a slow evacuation of the interior, a steady thickening of the boundaries. If you color the flow lines, they look like ripples moving outward from a pebble dropped into a pond, but here the ripple is negative, the pond draining from its middle. Over cosmic time, this outflow can reach hundreds of kilometers per second. For example, in the Boots void and in our own KBC region, galaxies near the center drift outward at roughly 200 and 400 kilometres relative to the cosmic rest frame. Astronomers have measured this directly, using data from the Cosmic Flows 3 catalogue, a vast census of galaxy distances and peculiar velocities. By comparing redshift-based motion with independent distance indicators like the Tully-Fisher relation and Type Ia supernovae, researchers can map how galaxies deviate from the overall Hubble flow. The pattern is unmistakable. Velocities inside voids diverge vectors pointing outward like spokes from a hub. This is gravity's quiet rebellion. It has not changed its law, only the gradient of mass has changed its stage. Where mass is missing, expansion wins. The energy of the cosmic vacuum pushes outward, while the gravitational pull from denser surroundings gives the same result, a slow, persistent outward drift. The boundary between void and filament becomes a kind of cosmic shoreline where opposing currents meet. In these simulations, time acts as a sculptor. Early on, small underdensities expand a little faster than average. As they empty, their interiors thin, amplifying the imbalance, making them expand faster still. The feedback loop continues for billions of years. Gravity at the walls grows, the interiors relax, and the universe's large-scale structure becomes a network of breathing bubbles, each one exhaling matter toward its edges. To visualize it, picture a field of soap bubbles frozen in time, then imagine unfreezing them. The films between bubbles thicken as each cavity swells. The junctions where three bubbles meet our galaxy clusters become bright nodes pulling the universe's scaffolding taut. The motion is almost organic, a slow pulse through the fabric of space-time. Observations back this picture with eerie precision. Surveys like Sloan Digital Sky Survey SDSS and DSR have mapped enormous contiguous voids and measured their average density contrast, about 20% lower than the cosmic mean. When the observed galaxy motions are compared to model predictions, the data align, showing that void interiors indeed expand faster by roughly the same fraction. Gravity's reverse flow is now not just a simulation artifact, but a measured phenomenon. On a cosmic scale, this outflow subtly biases how we interpret motion and distance. A galaxy drifting outward inside a void recedes faster than it would in a uniform universe. From our perspective within the KBC region, that means everything around us looks like it's accelerating slightly more than average. The same mechanism that empties voids therefore mimics dark energy's push, a coincidence that may help explain why the local Hubble constant appears high. and yet it's humbling. What we call repulsion is really the universe returning to equilibrium. Matter flees emptiness because there is nothing left to hold it. Gravity doesn't fail, it simply redirects its effort toward where the mass still resides. In this slow-motion evacuation, the cosmic web breathes. Every filament gains what each void relinquishes, like tides exchanging momentum across a trillion light-year sea. The equations of general relativity still rule every motion, but within the hollows of space their melody shifts key from the heavy chords of attraction to the lighter rhythm of release. Next we follow that rhythm to its frontier, the threshold where gravity's pull finally yields entirely to the vacuum's push. An expansion becomes not a tendency, but a destiny. There is a line as old as modern cosmology that we have rarely dared to cross the assumption that the universe, when averaged over large enough scales, is the same everywhere. We call it the cosmological principle, homogeneous and isotropic on the grandest canvases, and we lean on it every time we convert redshift to distance, brightness to age, map to meaning. But as our surveys deepen and our statistics sharpen, the line trembles. The sky's long wavelength quirks, the improbable hollows, the outsized structures, and the stubborn tensions whisper the same unease. Perhaps the universe is not as uniform as we pledged it must be. Start with the local anomaly, the KBC region, a super void-like underdensity wrapping our neighbourhood for hundreds of megaparsecs and more. Galaxy counts from all-sky infrared catalogues and optical redshift surveys agree locally we have less matter than average by on the order of 20%. That would be a curiosity if it ended there, but the implications bleed outward. A large underdensity expands faster bias's distance ladders and tilts the Hubble constant high. If our yardsticks sit inside a swelling bubble, then the local truth can diverge from the global. The principle does not forbid statistical flukes, but the size and depth of our hollow press against its margins. Zoom out and the sky itself becomes lopsided. The cosmic microwave background, the earliest light, our cleanest test of primordial uniformity, carries a faint hemispherical power asymmetry, a preference for slightly stronger fluctuations on one side of the sky than the other. There is also the notorious large-angle alignment, the so-called axis, in the CMB's lowest multipoles. Each effect alone might be noise. Together they read like subtle fingerprints of a universe whose grand average conceals long wavelength structure. Add the deep cold spot consistent with a supervoid imprint along the line of sight, and the map of everywhere the same begins to look textured. Then there are the outsized structures in the galaxy distribution. Great walls and quasar groups that test our intuition about the maximum coherence length of the web. These are not proofs of principle breaking on their own. LCDM tolerates unlikely events. But a pattern of improbabilities is its own kind of evidence. When the rare keeps recurring supervoids a little too deep, alignments a little too tidy, we're compelled to ask whether our smoothing scale is honest or simply hopeful. On intermediate scales, the universe resists calibration in quieter ways. Weak lensing amplitudes inferred from galaxy shape surveys have at times sat a little lower than the fluctuation strength implied by the CM, a mild discord known as the S8 tension. Meanwhile, the Hubble tension, local 73 verse, early universe 67 kilomantos towards S1, MPC1, refuses to fade with better data. None of these discrepancies alone overturns homogeneity, but they all rhyme with the same refrain position and environment matter more than our simplest idealizations admit. This is where the stakes come into view. The cosmological principle is not a decorative axiom. It is the load-bearing wall of our inference pipeline. Averaging matter density to a constant allows one set of equations to describe expansion everywhere. It lets us compress a wildly lumpy cosmos into a smooth space-time, and then reintroduce lumps as perturbations. If the averaging fails, if inhomogeneities do not wash out cleanly at the scales, we assumed then the step from real sky to model sky becomes non-trivial. Small biases can accumulate into back reaction, the idea that the way we average many local expansions is not equivalent to a single global expansion. Cosmologist Thomas Bucket has spent years formalizing this worry. In his language, the Einstein equations do not commute with spatial averaging. If you average first and then evolve, you need extra terms, kinematical back reaction, and curvature evolution to capture how lumps and voids collectively steer the cosmic flow. In a perfectly uniform universe, those terms vanish. In ours, they may whisper. Buckett's warning rendered plainly is that our smooth model might be missing the cost of smoothing. Astrophysicist Joseph Silk has framed the challenge more bluntly. The cosmological principle is sacred not because Einstein blessed it, but because everything we do depends on it. Break it, and we must revisit the entire hierarchy of inference from standard candles and rulers to growth rates and gravitational lensing checking, which conclusions were robust to environment, and which were artifacts of misplaced symmetry. Even when Silk defends the principle as a useful approximation, he keeps its conditional clause in the light approximation, not revelation. Science communicators like Ethan Siegel have emphasized the same stakes for a broader audience. If we turn out to live in an atypical patch, a supervoid with unusual flows, then many clean comparisons, local versus early near versus far, become apples and oranges. Our best fit parameters may remain right for the universe at large, but become wrong for where we sit. And from the perspective of a species measuring everything from a single world line, that distinction matters more than pride prefers. So what would a principle breakdown look like, not philosophical but practical? It would begin with environment-dependent expansion, void regions showing systematically higher local Hubble rates and slightly altered distance redshift relations compared to filamentary ones. It would be reinforced by large angle anomalies in the CMB that resist all instrumental and foreground explanations, while correlating with supervoid supercluster distributions. It would include a census of structures whose sizes and coherences push the tails of LCDM's probability curves harder than comfort allows, and it would cohere across independent probes' BAO scales that drift subtly with environment, time delay lenses that prefer one expansion rate, while standard Siren's gravitational wave distances prefer another, supernova Hubble diagrams that straighten when conditioned on the density field through which their light travelled. Crucially, it would be predictive, not merely accommodating. If averaging truly matters, then fully relativistic simulations that resolve void wall contrasts should reproduce a measurable offset between environment-conditioned clocks and rulers, and those offsets should match the observed tensions in magnitude and sign. If inhomogeneous dark energy or modified gravity play a role, their fingerprints should appear in void lensing redshift space distortions and the evolution of the BAO ruler. Perhaps the principle survives the trial. Perhaps Euclid's billion galaxy map and Rubin's decade of weak lensing time series restore uniformity with tighter error bars and elegant vindication of the old assumption. Or perhaps the verdict is subtler, not a guilty shattering, but a narrowing of scope. Homogeneous and isotropic as a first-order truth conditional on scale and on how we average, environment-dependent corrections promoted from footnote to formula. If that is where we land, the sky does not fall. It changes resolution. Our cosmology would become explicitly two-layered, a global backbone, the early universe parameters that pattern the CMB, and a local, dressing the way voids and walls bias the rulers and clocks we actually hold. The equations are the same. The inference pipeline grows honest about context. In the quiet cadence of this series, the message is not scandal but maturity. The cosmological principle taught us how to begin a smooth score under the universe's first movements. Now the instruments are sensitive enough to pick up the counter-melody, the lilt of emptiness, and the weight of walls the way local structure leans on the global tempo. To admit that is not to abandon Einstein. It is to complete him, to recognize that the beauty of a law lives not just in its simplicity, but in the grace with which it accommodates the world it describes. If the universe is not exactly the same everywhere, then what we learn from where we are becomes even more precious. Our hollow is no disgrace, it's a window. Through it, we can test how far uniformity carries and where the fabric starts to show its weave. And from that weave, a deeper pattern may emerge, one in which the average is still a guide, but never again a blindfold. In the next part, we step from foundations to futures. If the vacuum itself varies, and the web's hollows expand faster than its walls, what becomes of the long tomorrow? Does the universe drift into a seamless dark, or does the breath of dark energy change with age? There is a gentler explanation for many of our cosmological tensions, one that does not demand new particles or a rewriting of gravity. It is also the least glamorous. We may simply be unlucky. In the grand raffle of the cosmos regions, dense and sparse, hot and cold, fast and slow, we drew a ticket that sits toward the tail of the distribution. Not impossible, just rare. This is the quiet doctrine of cosmic variance. Even if the universe is on average homogeneous and isotropic, any single patch of it, even one as enormous as our observable sky, will wander around that mean, and we only ever get to live in and measure one patch. Think about tossing a fair coin 10 times. You know it is 50-50, yet runs of heads happen. With 1,000 tosses, the imbalance shrinks. With 1,000,000, it shrinks further. In cosmology, our coin tosses are the fluctuations in density and temperature spread across the larger scales. But here the analogy breaks, we can't toss again. There is no second universe to average over, and even within ours there is a horizon, a spherical boundary beyond which light hasn't had time to reach us. All our statistics must be built from a single sky, observed once filtered through one history. The result is a permanent flaw under our precision. Cosmic variance sets the limit to how exactly we can know certain quantities, no matter how perfect our instruments become. You can see this most clearly in the cosmic microwave background. On small angular scales, many hot and cold blotches across the sky, we have millions of independent samples. The averages behave nicely, uncertainties shrink, but on the larger scales, the vast slow undulations corresponding to the earliest grandest modes, there are only a few independent patches on our whole sky. Those low harmonics carry built-in uncertainty simply because there aren't many of them to average. If they look slightly lopsided or aligned or quiet, we must always ask, is this new physics? Or did we just draw a quirky sample from a fair distribution? The same humility applies to the cosmic web. Even if the universe's statistical recipe is fixed, tiny primordial ripples with a given amplitude and spectrum randomness still decides exactly where deep voids and thick walls appear. There will always be places with a little more structure and places with a little less. If our own address lands in a supervoid, then our local measurements of expansion, clustering and brightness can be skewed by that draw. That does not violate the global recipe. It simply means we are sampling it from an atypical seat. This is the cosmic lottery view of the KBC region. The standard cosmology says such large underdense domains are improbable, but not forbidden. A world somewhere must live there. Perhaps that world is us. From within, galaxies would drift outward a bit faster than average distances inferred from supernovae would stretch slightly more, and the local Hubble constant would read high, exactly the flavour of the tension we debate. In the same spirit, the CMB hemispherical asymmetry and the famous cold spot could be long-wavelength statistical hiccups, amplified by the fact that we have only one sky to consult. But to lean on cosmic variance is not to shrug, it is to quantify. Cosmologists do not wave away anomalies, they compute the odds. How often would a universe like ours, obeying the best fit parameters of the early plasma, produce a super void as deep as KBC somewhere? How often would the largest CMB modes align as they appear to on some sky? What is the expected spread in local Hubble measurements if you embed observers at random locations across 1 billion simulated universes? These are not rhetorical puzzles. They're experiments run on supercomputers producing distributions against which we can place our single realization us. When we do this, a theme emerges. Many of the oddities that unsettle us fall in the realm of uncomfortable but not impossible. 2 or 3 sigma quirks, rare, yes, but unsurprising in a field that measures thousands of things. Statisticians call this the look elsewhere effect. If you inspect enough features, some will look special. Add in the subtler biases, Malmquist bias, bright things are easier to find. Eddington bias, noise scatters, counts upward. More than downward selection effects in survey footprints and the tails of the distribution fatten. What begins as scandal can end as the cost of looking hard. The challenge is existential as much as technical. Physics craves repeatability. Cosmology offers one experiment. The cure is ingenuity. We simulate many universes and ask where we sit among them. We split the sky in different ways, rotate coordinate systems, blind our analyses to avoid confirmation drift. We add independent rulers, baryon acoustic oscillations, weak lensing standard sirens from gravitational waves, time delay cosmography from lensed quasars. Each probe has its own pattern of variance. Their overlap cancels what any one method cannot escape. Where all agree, we trust. Where they scatter, we weigh the odds. Even so, cosmic variance never fully leaves the room. On the very largest scales, it is the final whisper. You cannot know this more precisely because the universe has not offered you more dice to roll. The cosmological principle, our faith in large-scale uniformity, is partly a statement about physics and partly an act of statistical modesty. We assume the average because we cannot sample beyond our horizon. It has served us spectacularly well, but it is also conditional. When anomalies cluster, we must ask whether we are paying the fair price of variance, or discovering a bias in our vantage or a crack in our model. There is also the matter of anthropic selection, soft and controversial but relevant. Life arises in particular environments, galaxies with metals, stars of certain lifespans, stable orbits sheltered from catastrophic bombardment. If such conditions correlate with certain large-scale neighborhoods, say quiet filaments near void edges where mergers are gentler, then observers will preferentially find themselves in specific kinds of cosmic regions. That does not grant special status to our address. It explains why certain unlikely addresses are more commonly observed. The sample of all locations is not the same as the sample of locations with eyes. So where does the cosmic lottery leave our present tensions? It offers a conservative triage. Before invoking modified gravity or evolving dark energy, price in the variance, simulate observer-to-observer scatter in HZU inside a lumpy web, propagate selection effects, test whether the joint pattern of discrepancies, not just their sizes but their directions, matches what variance predicts. If yes, the universe is reminding us that one sky is a noisy sky. If not, if the anomalies line up with the same sign across probes, the same dependence on environment, the same redshift evolution, then chance is no longer an elegant answer. At that point, the odds push us toward new ingredients or new inference. Cosmic variance does not lull, it disciplines. It teaches us to distinguish weather from climate realization from rule. It forces humility into our error bars and patience into our headlines. Most of all, it frames our solitude properly. We are a one-observer species reading a single edition of the universe printed once. Our tools are brilliant, our sample is small, and yet there is comfort here too. In a field built on distant light and delicate statistics, the existence of a hard limit is a kind of mercy. Beyond a point, the universe does not ask us to be sharper, only to be honest. We cannot roll the dice again, but we can learn the game so well that one roll suffices to hear the rules humming underneath. In the next part, we turn from chance to checks, how cosmologists braid multiple orthogonal measurements to escape the confines of a single draw, and how together they can tell luck from law when the sky itself will not give us a second try. Every structure we see, the walls of galaxies, the vast black hollows between them, even the KBC void that cradles our home, began as whispers in the quantum foam. Before stars, before atoms, before light itself, the universe was a mist of energy expanding faster than imagination could track. And within that mist, the tiniest quantum jitters, fluctuations smaller than a proton, were stretched by cosmic inflation into the scaffolding of everything to come. This is the strange lineage of emptiness. The voids we map today are the enlarged shadows of uncertainty itself. The inflationary beginning. Inflation is the brief, ferocious burst of accelerated expansion thought to have occurred in the first 10^3210 and 32 or 1032 seconds after the Big Bang. Whatever drove it, perhaps a scalar field dubbed the inflaton, smoothed the young universe to extraordinary uniformity, erasing any earlier irregularities. Yet it could not smooth everything. The quantum nature of that field guaranteed microscopic variations in energy density, random and ceaseless like foam on a wave. As inflation magnified space by a factor of at least 6, those microscopic ripples were frozen into the fabric of space-time, each one inflated to cosmic proportions. Tiny differences in density, parts per 100,000, became regions ever so slightly over or under dense compared to their surroundings. When inflation ended and normal expansion resumed, these frozen ripples became the blueprint for structure formation. From quantum noise to cosmic architecture, for hundreds of thousands of years after the universe remained a uniform plasma of light and particles. Sound waves rippled through it, compressing matter in rhythmic shells that would later leave the baryon acoustic oscillation pattern. Where inflation's quantum dice had rolled high, gravity found a head start. Matter accumulated. Where the dice had rolled low, matter lagged, leaving empty zones, the first sketches of future voids. When the universe cooled enough for atoms to form about 380,000 years after the Big Bang, photons decoupled, releasing the cosmic microwave background. Its faint temperature blotches are the direct photograph of those original fluctuations. Look closely at that sky, and you are staring at the birth map of every void. The darkest, coolest patches mark regions that began ever so slightly emptier. Over the next 13.8 billion years, those tiny absences expanded, deepened, and connected into the vast network of hollows we now chart. Simulations of quantum ancestry. Modern simulations trace this genealogy backward. Start with the observed pattern of galaxies and run gravity in reverse, and you can reconstruct the primordial density field. Then run it forward again under the laws of general relativity. The result is stunning continuity. The supervoids and filaments we see align perfectly with the peaks and troughs of the initial quantum spectrum measured in the CMB. The same ripples of vacuum fluctuation that once lived in a space smaller than an atom now span hundreds of millions of light years. The paradox of structure from silence quantum physics teaches that the vacuum is never truly empty. It seethes with virtual particles popping in and out of existence. Inflation amplified that microscopic restlessness into cosmic geography. What we call emptiness in the night sky is in a very real sense the echo of quantum noise from the universe's first instant. Every void is a memory of a low roll in the primordial dice. Even the statistics match the distribution of void sizes follows the same nearly Gaussian power spectrum predicted for inflation's fluctuations. The amplitude of those initial ripples, about 1 part in 100,000, is exactly what gravity needed, small enough to preserve early smoothness, large enough to let the universe grow lumpy over billions of years. If the quantum seeds had been slightly weaker, no galaxies would ever have condensed. Slightly stronger, and the cosmos would have collapsed into a tangle of black holes. Between those razor-thin extremes, reality found its balance. The poetry of origins. So when we map the cosmic web today, the filaments glowing with galaxies, the voids yawning between them, we are not seeing two separate phenomena, matter and emptiness, but two phases of one primordial field. The bright threads are the crests of the first quantum waves, the voids are their troughs. The pattern is not random chaos, but the fossilized vibration of a universe learning its own rhythm. In this sense, quantum mechanics did not merely dictate the micro-world, it sculpted the macro-world. The same uncertainty that governs electrons in an atom carved the universe's largest architecture. The smallest possible cause gave rise to the largest possible consequence. What began as flickers of vacuum energy became galaxies' clusters, and the great dark lungs of space that now exhale expansion. The universe's vast emptiness is thus the most ancient thing of all, older than light, older than form, a magnified silence that still remembers the first whisper of quantum chants. In the next part, we follow that whisper forward, how those ancient ripples continue to shape today's expansion, and whether the same quantum restlessness might one day seed the universe's next transformation. In the beginning, the universe was smaller than an atom, and then almost instantly it wasn't. In a time shorter than imagination can measure, around 1035 seconds after the Big Bang, space itself began to inflate, expanding exponentially, doubling in size again and again, faster than light could ever hope to chase its own shadow. In that breathless fraction of a moment, the cosmos grew by a factor of at least 1026, stretching from subatomic to cosmic in a single silent surge. This is inflation, not an explosion into space, but an explosion of space. Its driver, according to theory, was a field of energy filling the early universe, call it the inflaton, a kind of cosmic battery that temporarily dominated the energy budget. While it held sway, its negative pressure acted as a repulsive form of gravity, forcing every point in the universe to rush away from every other, smoothing out curvature, ironing over any primordial wrinkles, and cooling the cosmos by pure expansion. The miracle of inflation is not just what it explains the uniformity of the sky, the near-flat geometry, the origin of structure, but how it connects the smallest possible physics to the largest possible pattern. Because even as inflation smoothed the universe overall, quantum mechanics refused to stay silent. Frozen ripples in the fabric, quantum fields cannot rest completely. They fluctuate always and everywhere. Tiny energy variations in the inflaton field cause space itself to expand ever so slightly faster in some regions than in others. At first, these variations were unimaginably small differences of perhaps 1 part in 1050. But as inflation proceeded, those subatomic jitters were stretched to macroscopic scales, growing by 30 orders of magnitude in size. Then, as inflation ended and the universe reheated into a hot soup of particles, those stretched ripples were frozen into the density of the newborn cosmos. Each fluctuation became a slightly overdense or underdense patch, an embryonic seed of every future galaxy and void. The randomness of quantum noise had been translated into the geography of matter. You can picture it as an immense freeze frame. Inflation acted like a flash photograph of quantum chaos, capturing patterns that would normally cancel out in the blur of time. When expansion slowed and normal physics resumed, those frozen waves became the initial conditions for everything that followed. The crests would attract matter, the troughs would repel it. Gravity would then spend the next 13.8 billion years amplifying the contrast, turning invisible quantum wrinkles into the grand architecture of the cosmic web. The Planck map, the fossilized echo today, we can still see those frozen ripples. They are written across the cosmic microwave background CMB, the afterglow released 380,000 years after the Big Bang, when the first atoms formed and light could travel freely. The Planck satellite has mapped this radiation to exquisite precision, a sky speckled with tiny temperature variations only about 1 part in 100,000. Those faint blotches are the direct imprint of inflation's quantum fluctuations, preserved as if on ancient papyrus. Each slightly warmer patch corresponds to a region that was once denser, its photons trapped a bit longer in a deeper gravitational well. Each slightly cooler patch marks a shallower region, the germ of a future void. The Planck map is in essence a baby picture of the universe, the oldest image ever taken, showing a cosmos still carrying its quantum fingerprints. The statistical pattern of those blotches tells an extraordinary story. When Planck measured their power spectrum, how fluctuation strength varies with scale, it found an almost perfect scale invariant form, the same pattern repeated from large angles to small, just as inflation predicted. It also found that the fluctuations follow a Gaussian distribution consistent with random quantum noise. No sign of preferred directions, no built-in asymmetry, just a faint tilt, the famous red spectral index, showing slightly more power on large scales than small. That subtle tilt is exactly what simple inflation models anticipate the gentle decline of the inflaton's energy as it rolled toward its minimum. Even more telling are the polarization patterns Planck detected, minute alignments in the CMB's light caused by scattering during the universe's first moments. Their amplitude and orientation matched the ripple field inflation would produce. To this day, cosmologists comb the data for an even fainter signature, the B-mode polarization that primordial gravitational waves would leave another echo of inflation's violent birth. The search continues, but the basic framework quantum fluctuations frozen during exponential expansion has survived every challenge. From particle to galaxy, connect the dots forward, and the continuity is breathtaking. A ripple 1/4,000th, the width of an atom, becomes through inflation and gravity, a void 100 million light-years wide. A quantum fluctuation in the inflaton field becomes a supercluster of galaxies. Inflation's mathematics, built from Planck's constants and Einstein's curvature, unfold naturally into the scales we inhabit. The bridge between particle physics and cosmology is literal. Our galaxies are fossils of wave functions. In this sense, the night sky is not random, it's a record of quantum behavior writ large. Every filament of galaxies, every yawning void, every cluster of stars traces back to the same seed pattern, visible in Planck's temperature map. The connection between micro and macro could hardly be more intimate. The very same physics that makes electrons blur around atoms gave the universe its cosmic web. So when we speak of the architecture of the heavens, we're really describing the after effects of uncertainty. Inflation took the smallest known principle, the jitter of quantum fields, and stretched it across the entire sky, preserving it as the template for everything visible. In the next part, we follow those ripples as they continue to shape cosmic destiny, how the pattern of early fluctuations determines not just where galaxies formed, but how the universe's expansion will unfold in its far future, an echo of quantum breath still widening the voids between stars. At first glance, the cosmic microwave background seems to fulfill the dream of symmetry, a perfect featureless glow stretched over all directions, the quiet signature of a universe born evenly. But when Planck WMAP and COBE measured that glow in finer detail, microkelvins of difference, the symmetry began to tilt. The cosmos, it turned out, has a preferred direction, faint but persistent, etched into the oldest light we can see. The sky's strange tilt. The most famous of these oddities goes by a name equal parts humour and unease, the axis of evil. It first appeared in 2004 when astronomers analysing WMAP data noticed that the largest temperature harmonics of the CMB, specifically the quadrupole and octopole, seemed to align along nearly the same axis on the sky. Instead of random uncorrelated blotches, the biggest hot and cold regions were lined up, as if someone had brushed the universe in one direction before it cooled. That axis, roughly toward the constellations Virgo and Aquarius, doesn't match any local contamination, not the plane of the Milky Way, not scanning artifacts, not dust. it seems to belong to the cosmos itself. The probability of such alignment happening by chance in a truly isotropic universe is small, somewhere between 1 and 2% depending on assumptions. Not definitive proof, but enough to whisper that something about the early expansion might have favoured one orientation over another. The strangeness doesn't end there. Another anomaly, the hemispherical power asymmetry, shows that one half of the CMB sky has slightly stronger temperature fluctuations than the other. Imagine looking at Earth's weather map and finding that all storms prefer one hemisphere that's the level of oddity here. The discrepancy is only a few percent yet in a universe supposed to be statistically identical in every direction. Even a small bias stands out like a fingerprint on glass. Add to this the cold spot, a broad region in the southern hemisphere, where the CMB temperature dips about 70 microkelvins below average, and the pattern of perfect uniformity begins to look textured, almost scarred by its birth. Each effect alone might be dismissed as noise or coincidence. Together they form a persistent constellation of asymmetries across the oldest light. Possible origins. Cosmologists have spent 2 decades exploring explanations from the pedestrian to the profound. Foreground contamination remains the simplest, perhaps subtle microwave emission from interstellar dust, or the solar system leaked into the data. Yet multiple satellites, COBE's Yausmap, Planck, using different frequencies and instruments have all seen the same broad alignment. Statistical fluke is still possible. Cosmic variance guarantees that even a truly uniform universe will show random imbalances when observed once. The odds are low but not zero. Maybe we just drew a peculiar sky. Anisotropic inflation offers a deeper, more exotic explanation. If the inflationary field that drove the early expansion wasn't perfectly uniform, if it had a slight gradient, or coupled to another field that preferred one direction, then the resulting expansion would have stretched space unevenly, seeding a subtle axis in the density field. The direction of fastest expansion could imprint itself as a permanent tilt in the CMB's largest modes. In such models, the universe still obeys relativity, but its earliest breath carried a hint of asymmetry, like a balloon inflated faster along one seam than the others. Multiverse interactions take the speculation further. If our inflationary bubble was just one among many in a wider multiverse, then collisions between neighbouring bubbles could have left circular imprints or directional gradients in the CMB. These would appear as localised temperature anomalies or hemispherical modulations, exactly the kind of features we puzzle over. Though unconfirmed, several studies have searched the CMB for concentric ring signatures of such encounters. None decisive, but none completely ruled out. Topological relics from pre-inflationary physics, cosmic strings, domain walls, or other exotic defects might also create alignments or cold spots, though evidence remains elusive. Planck's verdict: uncertain symmetry. When the Planck satellite re-examined these anomalies with higher precision, it confirmed their existence but softened their drama. The alignments remain, but their statistical significance sits on the boundary of what might occur by chance. Planck's data suggest no gross violation of isotropy, yet they cannot fully erase the whisper that something directional lingers at the universe's birth. In the cautious language of cosmology, this is the tension between p-value and poetry. The numbers say probably coincidence. The mind seeing patterns traced across the first light wonders whether the universe remembers the way it expanded. The philosophical edge. If these asymmetries are real, the implications cut deep. A directional inflation would mean the universe has a cosmic axis, a kind of orientation in space, even if only statistical. That would quietly retire the cosmological principle's claim of perfect equivalence, replacing it with something more nuanced, almost uniform but born with a slight lean. In such a case, every galaxy, every void, every law of physics we know would carry that subtle bias, an invisible arrow embedded in the cosmic fabric. Some researchers like Dominic Schwartz and Glenn Starkman have noted that if inflation had a built-in anisotropy, it might explain not just the CMB alignment, but also why large-scale bulk flows, the collective motions of galaxy clusters, seem to point roughly in the same direction. Others caution that human brains are pattern hunters. Given one sky to analyse, we will always find axes alignments meanings. Yet the question remains irresistible: did the universe have a handedness at birth? Did one quantum fluctuation dominate its first instant of inflation, stretching space more along one line than another? Or are we merely seeing the statistical echo of a random patch mistaking chance for design, the view from humility? For now, cosmologists walk the narrow path between curiosity and caution. The asymmetries exist in the data, their interpretation remains open. Future missions, LIGHTBIRD, CMBS-4, and high-precision polarization studies may help decide whether the axis of evil is physics or coincidence. But there is also an aesthetic truth in the uncertainty itself. Even the most uniform thing we know, the afterglow of creation, is not perfect. It carries a slight asymmetry, a flaw that allowed structure to grow, stars to ignite, and us to wonder why. Without that imbalance, the universe would still be a smooth bath of light, too symmetrical for life to, even for thought. So perhaps it is fitting that the first light bears a scar. It reminds us that perfection was never the goal. Variation is the engine of creation. Next, we follow that asymmetry forward, how the same ripples that seeded galaxies also guide today's gravitational flows, and how the universe's faint directional bias may echo through its long future. Could gravity alone, the simplest of the cosmic forces, the quiet curvature of space-time, really sculpt a universe as intricate as the one we see? Could that single law, acting on uniform hydrogen for nearly 14 billion years, generate everything from the vast galactic walls to the yawning supervoids, from stars to consciousness itself? For decades, cosmology has answered yes. The LCDM model, lambda cold dark matter, has been the reigning champion of simplicity. 6 parameters, a handful of equations, and it reproduces nearly everything we can measure. The cosmic microwave background's detailed spectrum and peaks, tracing acoustic waves in the primordial plasma. The large-scale clustering of galaxies matching the statistics of the early ripples seen by Planck. The expansion history from the Big Bang to the present acceleration. Even the distribution of light elements born during the universe's first 3 minutes. In this model, gravity's steady pull acting on dark matter and ordinary matter alike amplifies tiny primordial density variations into the filaments, walls, and voids that now define the cosmic web. Dark energy, the L, adds the late-time acceleration, ensuring galaxies drift apart while local structures still coalesce. On nearly every testable front, LCDM works, and yet the closer we look, the more gravity's perfection begins to wobble, cracks in the smoothness. Simulations based purely on gravity plus dark matter and dark energy can reproduce the statistical texture of the universe, but not always its specific character. They produce too many small satellites compared to what we observe the famous missing satellites problem. They build central galaxy halos that are too dense cusp core tension. They predict a slightly slower local expansion rate than nearby supernovae imply the Hubble tension, and they underestimate how fast some massive galaxies formed the early giant problem revealed by JWST. Each discrepancy can be patched, add baryonic feedback here, tweak star formation efficiency there, but the pattern suggests something deeper. Perhaps gravity's simple averaging over an uneven universe misses subtle cumulative effects, the back reaction question. In 2000, cosmologist Thomas Buchert formalized an idea known as back reaction, that the uneven distribution of matter itself might feed back on the cosmic expansion. In Einstein's equations, space does not expand at a single universal rate. Dense regions collapse faster under gravity, while voids expand faster, their weaker gravity offering less resistance. Over time, these differences may not perfectly average out. If the voids occupy more and more of the total volume, as observations suggest, they could skew the global expansion rate upward, mimicking the effect of dark energy or altering the measured value of H0. In mathematical terms, the average of a curved field is not the same as the curvature of the average field. This nonlinearity means that even if general relativity holds everywhere, the universe's inhomogeneity can distort its overall dynamics. It is as if the cosmic orchestra contains many instruments playing slightly different tempos. The sum of those tempos may not match the conductor's simple beat. Back reaction theory asks, are we mistaking the combined improvisations of billions of galaxies for a single smooth symphony? Could dark energy or part of it be an illusion born of our averaging process? So far, the jury is divided. Detailed numerical experiments suggest that while local inhomogeneities do modulate expansion, the effect is probably modest, perhaps a few percent, not enough to replace dark energy entirely. But that few percent might matter, because the key cosmological tensions, the Hubble gap, weak lensing discrepancies, are also at the few percent level. If gravity's self-interaction with structure adds even a small correction term, it could reconcile models with measurements without invoking exotic new physics. Gravity's evolving reputation. Einstein himself once doubted that his equations could handle a lumpy universe. He favoured smoothness for simplicity. But nature is not smooth. The cosmic web is a tangled hierarchy of filaments, clusters and voids spanning orders of magnitude. Within that hierarchy, gravity is not static, it flows, folds, rebounds. Clusters act as brakes on expansion, voids act as accelerators. Each region's evolution subtly drags on or pushes against the others. The cumulative effect could, in principle, alter the mean expansion in ways we have yet to fully measure. When cosmologists simulate structure formation today, they typically use Newtonian gravity in an expanding box, a very good approximation for subhorizon scales, but not fully relativistic. New generations of simulations such as Gevolution, Gramsci's, and relativistic n-body codes attempt to fix that. They track how curvature and expansion interact non-linearly across billions of light-years. Early results hint that relativistic corrections and back reaction may indeed shift cosmological observables at the percent level, small but significant in an era where our precision is better than ever. Success, but not supremacy. So where does that leave gravity? Still majestic, still sufficient to build the scaffolding of the cosmos, but no longer beyond question. LCDM remains the most accurate large-scale map we possess, yet its perfection is slightly bruised. If inflation planted the seeds, and dark matter supplied the scaffolding, perhaps back reaction supplies the mortar, small adjustments born of unevenness, the feedback of reality on its own equations. It is a humbling notion that the universe's patchiness can alter the way the whole breathes. Gravity, far from being a passive architect, becomes a participant in its own work, reshaping its future behaviour. A new kind of symmetry. Maybe this is the next refinement in cosmic understanding. Instead of a universe obeying one global law exactly, we see a self-referential cosmos where local differences accumulate into gentle biases that ripple outward. Gravity's strength does not fail. It adapts to the distribution it creates. The web alters the field that spun it. In that view, the cosmos is not a marble statue carved once, but a living sculpture that sags, stretches, and subtly reshapes itself under its own weight. Next, we explore how that living sculpture evolves toward its future, whether the interplay between matter and vacuum, between gravity and dark energy, leads to eternal acceleration, a gentle slowing, or perhaps a second act of collapse and renewal. If you could strip the universe of everything visible, every star, planet, nebula, and galaxy, the architecture would still remain. The grand design, it turns out, is not built from light, but from shadow. Invisible halos of dark matter, vast, cold, collisionless, are the real scaffolding of the cosmos. They outweigh ordinary baryonic matter by roughly 5-1. Where these halos gathered, first gravity deepened the potential wells that drew in gas-birthing galaxies. Where they were sparse, expansion raced ahead, creating the great cosmic cavities we call supervoids. The visible universe is merely a thin frosting on an unseen lattice. The hidden framework in LCDM dark matter plays the starring role. It clumps early because it does not feel radiation pressure, forming a nearly invisible web of filaments, hundreds of millions of light-years long. Ordinary matter, protons and electrons still locked in the hot plasma of the early universe could only fall into those wells once it cooled enough to recombine. The first stars ignited at the nodes of that pre-existing skeleton. Each galaxy today sits inside a halo of dark matter that may extend 10 times farther than its starlight, like an unseen sphere of gravity holding its spiral together. Clusters are simply halos of halos. Even the vast walls that separate supervoids are threads of overlapping dark matter filaments, faintly traced by the galaxies that formed along them. What voids reveal? Yet in the deepest voids, where dark matter density drops by 80% or more, the model's simplicity begins to fray. Voids should be almost empty, but not entirely inert. LCDM predicts how quickly they expand, how sharply their edges form, and how the galaxies within them drift outward. Observations from the Dark Energy Survey, SCDSS, and Cosmic Flows catalogues show that real supervoids may expand slightly faster and grow slightly emptier than simulations expect. Some seem to tug on surrounding space with more vigor than gravity alone should allow. This discrepancy might be noise, or it might signal that Einstein's averages, the smooth equations of general relativity applied across lumpy matter, are missing a small but crucial term. When space-time is curved unevenly, the act of averaging curvature is not the same as the curvature of the average. In dense regions, gravity slows expansion. In voids, it releases it. If voids dominate the cosmic volume as they now do, then the universe's large-scale acceleration could be enhanced by its own inhomogeneity, not just by dark energy. In other words, the supervoids might be showing us the limits of Einstein's simplification. His equations assume a uniform fluid of matter, but the real cosmos is a frothy sea of extremes. The underdense spaces behave almost as if gravity is turned outward, producing a local acceleration field that subtly mimics dark energy's push. Searching for the missing ingredient. Some theorists propose that we need to refine gravity, not replace it, incorporating the feedback of uneven density or perhaps small relativistic corrections that accumulate over billions of years. Others suspect that the missing ingredient is not mathematical, but material dark matter itself might be more complex than we thought. If it interacts faintly with itself, colliding, scattering, or forming a superfluid phase, then the shapes of voids and halos could shift in just the way observations suggest. A self-interacting dark matter model, for example, naturally produces rounder voids and less cuspy halos, aligning better with data while preserving the cosmic web skeleton. Still others look to modified gravity theories, Monde-Tevez, emergent gravity FR models that alter how curvature responds to low-density environments. In these schemes, the apparent extra acceleration in voids could emerge not from unseen mass, but from the way space-time geometry behaves when matter thins beyond a critical threshold. Whatever the answer, supervoids are the proving ground. They are laboratories where baryonic noise fades where the pure geometry of the universe, its raw expansion, can be measured directly through weak lensing patterns, integrated Sachs-Wolf signals, and the motions of galaxies within. If Einstein's averages truly need amendment, the evidence will surface first in the silence of these hollows. The quiet challenge dark matter built the frame. Gravity filled in the pattern, yet the hollows between them whisper of something more. The cosmic web may not be just the imprint of invisible mass, but the consequence of how space-time itself behaves when it stretches too thin. Perhaps the missing ingredient is not another particle nor a new constant, but a deeper understanding of the dialogue between matter and geometry, how the uneven weight of existence bends the rules meant for a smooth universe. In the next and final part, we gather these threads, the voids, the variants, the living vacuum, into one closing reflection. What it means to inhabit a cosmos built on absence, and how in measuring that emptiness we come to understand ourselves. In physics, laws are promises, assumptions that the same rules apply everywhere. For a century, Einstein's general relativity has kept its promise spectacularly, explaining everything from the precession of Mercury to the merger of black holes. Yet on the largest scales and in the darkest places, supervoids, and the outer edges of galaxies, gravity seems to hesitate as though it has begun to second-guess itself. The cosmic evidence is clear enough: galaxies spin too fast for their visible mass. Clusters hold together with more gravity than their matter supplies. Voids expand more freely than standard equations predict. The usual answer is to add something unseen: dark matter and dark energy, and the LCDM model does so with remarkable success. But there remains an audacious minority of physicists who ask a different question. What if the laws themselves bend the heresy that won't die? In the 1980s, Israeli physicist Mordechai Milgram proposed a bold alternative. Maybe gravity changes its behavior when acceleration drops below a tiny threshold, about 10 test MES2. This idea, called modified Newtonian dynamics, or MOND, replaces unseen dark matter with a tweak to Newton's second law. In strong fields around the Sun inside galaxies, it agrees with normal gravity. But in the weak fields of galactic outskirts, the force becomes stronger than Newton or Einstein would allow, keeping stars in orbit without invoking invisible mass. MOND's simplicity is seductive. It predicted flat galaxy rotation curves before they were fully measured, and it naturally reproduces the Tully-Fisher relation, linking a galaxy's luminosity to its rotation speed. Yet it struggles on larger scales. Clusters still seem to require additional unseen mass, and MEAND by itself lacks a relativistic framework, one that can handle lensing cosmological expansion and the early universe CMB. TVES, giving relativity back its voice. To fill that gap, Jacob Bekenstein, a student and later critic of Einstein's orthodoxy, devised TVES tensor vector scalar gravity in 2004. It restores relativity to MOND by adding two new fields: a scalar that controls the modified acceleration, and a vector that introduces a preferred frame. Together with the usual tensor of Einstein's geometry, these fields mimic dark matter's gravitational pull while remaining purely geometric. TVIS can produce realistic gravitational lensing and a passable cosmology, though it too faces challenges matching the fine details of the CMB and large-scale structure. Still, it proved a point-modified gravity could be made consistent with relativity, at least in principle. FR gravity tweaking the curvature itself. Another family of theories alters not the content of spacetime, but the way spacetime curves. In Einstein's equations, curvature is proportional to energy and momentum built from the scalar RR, the Ricci curvature. In FR models, physicists replace that simple linear term with a more flexible function, FRF. The result is an effective self-modulating gravity, stronger in some regimes, weaker in others. Certain choices of FR can mimic cosmic acceleration without invoking dark energy. Others adjust the growth rate of structure to fit observations of voids and filaments more closely. Unlike M-on-the-FR, gravity can reproduce most of LCDM's successes while introducing only one new parameter. Its challenge lies in passing local tests in the solar system, where gravity must revert precisely to Einstein's form. To hide the modifications here, theorists invoke screening mechanisms such as the chameleon effect, in which the extra curvature term becomes dormant in dense environments, but active in emptiness. In this view, voids are not just empty, they are unscreened where the true enhanced form of gravity can show itself. Scalar tensor and emergent frameworks. A broader class of ideas, scalar tensor theories, includes Brans-Dicker gravity quintessence fields, and more recent Galilean and Horndeski models. These introduce a scalar field that couples to curvature, allowing gravity's strength, the effective Newton's constant, to vary with time or environment. Inside dense regions, the field's effect is suppressed. Inside voids, it grows, driving faster local expansion and potentially explaining the apparent overfreedom of supervoids without invoking exotic energy. Other approaches go further still. Entropic or emergent gravity, championed by Eric Verleen, imagines gravity not as a fundamental force at all, but as a statistical effect of information encoded on spacetime horizons. In this picture, the extra dark gravity arises naturally from the universe's storage of information, an echo of quantum thermodynamics that becomes visible at galactic scales. The theory remains young, but its mathematics reproduces Mond-like behavior and hints at a bridge between relativity and quantum mechanics. Gravity's flexibility under scrutiny. Each of these frameworks shares a motive to recover simplicity. Instead of adding invisible ingredients, they adjust the recipe of spacetime itself. The challenge is that gravity is obstinate. It passes every laboratory and solar system test with exquisite accuracy. Any new theory must reduce to Einstein's in all familiar settings and diverge only in the extreme, the edges of galaxies, the depths of voids, the dawn of cosmic expansion. That narrow window makes the quest both difficult and alluring. Upcoming surveys, Euclid-Vera-Rubin Observatory, Roman Space Telescope and CMB-S4 will map the growth of structure, the lensing of voids, and the slip between light's curvature and matter's motion with sub-percent precision. If gravity ever changes its mind, these instruments will catch it in the act. Already, some FAR models predict slightly stronger lensing across underdense regions. Scalar tensor versions forecast time-varying gravitational constants, measurable in pulsar binaries. Each anomaly, each asymmetry becomes a possible confession. A philosophical reversal. There is poetry in the idea that gravity, the force of unity, might itself be contextual strengthening, where matter gathers relaxing where it thins. It would mean the universe's structure does not merely follow the rules, it shapes them. Einstein taught that mass tells spacetime how to curve. These new theories whisper a revision. Perhaps the pattern of that mass tells gravity how to behave. If true, then every void is an experiment, each one a region where gravity reveals more of its personality. The emptier the space, the freer the law becomes. In that emptiness, we might glimpse the next evolution of physics, a cosmos where the constant of attraction is no longer constant at all, but part of a deeper self-adjusting conversation between matter, geometry, and the quantum vacuum. Next, in the final reflection, we return from theory to wonder to the human meaning of living inside a universe that may be both lawful and alive, predictable, yet self-correcting, a cosmos whose silence still shapes its song. The next few years will bring the most daring experiment in cosmology's history, an experiment without laboratories conducted entirely in the dark. For the first time, humanity will attempt to test Einstein's law of gravity, not around stars or black holes, but across the voids between galaxies where his equations have never been confirmed. Here in the deep cosmic hollows, the familiar pull of space-time weakens, dark energy breathes, and rival theories of gravity wait to be judged. The instruments of judgment, 3 great missions. Euclid, Nancy Grace Roman, and Deci form the triad of this cosmic tribunal. Each observes a different clue in the same invisible drama. Euclid, launched by ESA, peers across 10 billion light-years, mapping the weak gravitational lensing of billions of galaxies. By measuring how their shapes are minutely distorted by intervening matter, Euclid will chart the cosmic shear field, a 3D atlas of how space-time itself bends. Einstein's general relativity makes a clear prediction. The lensing strength and the growth of structure should follow the same tempo governed by one universal constant of gravity. But in modified gravity scenarios, FRTVs or scalar tensor models, the two begin to drift apart. Light curves differently from matter, voids lend slightly less filaments, slightly more. If Euclid detects that slip even by a few percent, it would be the first hint that gravity changes its tune when space grows thin. The Roman Space Telescope, NASA's companion to Euclid, will go deeper still. Its wide-field instrument will capture exquisite images of distant galaxies, measuring the cosmic acceleration through both lensing and supernovae. With its sensitivity, Roman can watch the geometry of the universe evolve over time, testing whether dark energy's strength truly stays constant. If the acceleration rate appears to depend on environment slower, through walls, faster through voids, the variable vacuum hypothesis will shift from speculation to evidence. Meanwhile, on the ground, the dark energy spectroscopic instrument Deci will act as cosmology's speedometer. By taking spectra of more than 40 million galaxies and quasars, Deci measures their peculiar velocities, the subtle deviations from the smooth Hubble flow caused by gravity's tug. In general relativity, these velocities trace the density field in a predictable way. More mass, more motion. But modified gravity theories alter that relationship. If galaxies and voids are drifting outward faster than expected, or clusters are collapsing slower, it means the law linking curvature and matter has shifted. Together, these missions will weave a web of cross-checks geometry from lensing kinematics, from velocities and history from supernovae. Each probe measures a different aspect of gravity's grip on the universe, and only if all 3 align will Einstein's century-old promise survive unbroken. The stakes. In 1919, the bending of starlight during an eclipse made Einstein a legend. The coming decade offers his second eclipse, this time not of the sun but of certainty itself. If Euclid, Roman and Deci find that the curvature of light and the motion of matter agree to better than 1% general relativity, will emerge not just undefeated but immortal, its reach verified across 30 orders of magnitude in scale. The same law that guides an apple's fall will have passed trial in the vacuum between galaxies. But if the data diverge, if the lensing pattern shows more or less bending than the growth of structure predicts, then the universe will have spoken in a new dialect. The discord could be subtle, perhaps the gravitational constant changes with redshift or voids, expand more vigorously than Einstein's equations allow. Even a mild mismatch between the gravitational slip parameter and the general relativistic value of 1 would hint that the fabric of spacetime hides new degrees of freedom. The first cracks might appear as quiet tension in the data, a lensing map that refuses to match the clustering map, a cosmic shear amplitude that drifts systematically high or low. Analysts will spend years verifying it, checking for dust instrumental biased statistical flukes. But if the signal persists, then the conclusion will be impossible to avoid. The most tested theory in physics will need amendment. The possible futures. In one timeline, Einstein's equations hold firm. Dark matter and dark energy remain the unseen sculptors, and the deviations we've noticed, the Hubble tension, the asymmetric voids dissolve into measurement quirks. The triumph would be profound, a single theory spanning from black hole singularities to the edge of the observable universe. In another timeline, the data break the mold. Gravity's pull weakens or strengthens with density. Light curves differently from matter. The cosmic acceleration varies by environment. The consequences would be revolutionary. New fields, new particles, or perhaps a quantum origin for the vacuum itself. Inflation and dark energy would become chapters of the same deeper physics bound by a variable geometry. Cosmology would enter its post-Einsteinian age. Either outcome transforms us. If Einstein prevails, we learn that nature's logic is even more elegant than we feared. If he falters, we glimpse a universe more alive, more self-correcting, a cosmos still writing its own rules as it expands. The narrative suspense picture. It billions of faint galaxies plotted into 3D space, forming a lattice of glowing dots across the known universe. Supercomputers hum, calculating the subtle flecks of light through billions of light years. On the screens of Euclid's control room in Darmstadt, the first weak lensing maps assemble. Filaments, here, voids there, each distortion, a fingerprint of gravity itself. In California, DESI's telescopes feed spectra to analysts comparing motion against mass. Somewhere in those terabytes may lie a small but fateful mismatch, an imperfection in Einstein's mirror. If the curves diverge even slightly, the news will ripple through science like a gravitational wave. It will mean that our most cherished constant, the geometry of reality, has been caught changing its mind. For now, the instruments are silent, the data still streaming home. We do not yet know which universe we inhabit, the faithful one ruled by Einstein's unbroken symmetry, or the flexible one guided by evolving laws. The answer will come not in thunder or revelation, but in the gentle tilt of distant light, the whisper of the cosmos judging its own design. Next, we close this journey through the hollow, the final reflection on what it means to dwell in a universe that may not be constant, and to find in its variability a mirror for our own restless search for truth. Across all our maps and measurements, from the flicker of ancient microwaves to the lensing of distant galaxies, a new picture is emerging. The universe may not be a single uniform equation written across the sky. It may be a mosaic, a quilt of regions, each obeying the same general laws, yet each living them slightly differently, its own tile in a cosmic pattern, too vast to see all at once. For a century, we have modeled the cosmos as one continuous fabric, gravity, constant dark energy, uniform, the same physics everywhere. That assumption, the cosmological principle, was our compass. But as our observation sharpened, the sky begins to resemble not a smooth sea, but a patchwork filaments dense as stone voids, light as breath, each expanding, aging, and even ticking through time at its own pace. A universe of local truths. Within the filaments and clusters, gravity reigns unchallenged. Galaxies wrestle in slow orbits, dark matter piles. High time runs a little slower in the deep wells of curvature. Here, Einstein's equations hold with exquisite precision. But move into the voids, the underdense oceans that fill most of the universe's volume, and the story changes. Expansion quickens, clocks tick faster, dark energy's influence grows. The cosmic constant no longer feels constant. Its grip strengthens where matter thins. Even light itself bends differently through such emptiness scattering, less arriving a little brighter or dimmer than expected. What we once called the universe may be better described as universes within a universe, domains of slightly distinct curvature and density, each adding its own rhythm to the grand ensemble. The equations of general relativity allow for such variation. It is our human desire for symmetry that once smoothed them away. Now, with Euclid, Roman, and DESI mapping billions of galaxies, those variations step into view, a cosmic atlas, coloured not by fantasy but by measurement, a patchwork of physics. If the cosmos truly behaves as a mosaic, then gravity, dark energy, and matter are not static ingredients, but fields that respond to environment. In dense regions, screening mechanisms may hide extra gravitational terms, making Einstein's laws appear exact. In emptier ones, those hidden terms awaken, gently modifying how expansion unfolds. This patchwork behavior could reconcile long-standing tensions, the higher local Hubble rate, the slower global expansion, the lopsided power in the cosmic microwave background. Each tile tells a slightly different story, but together they compose a coherent image. Some theorists describe this picture as a multi-phase universe, like water existing simultaneously as ice liquid and vapor, depending on pressure and temperature. Space itself may have analogous phases, bound, balanced, and free. In clusters, space-time is cold and rigid. In voids, it becomes warm and flexible. The average of those conditions yields the cosmos we observe, but no single phase captures the whole truth. In the language of mathematics, this is a universe governed not by a single constant, but by a field of constants values that vary smoothly with density and time. Newton's G Einstein's Alle, even the fine structure constant, could in principle drift ever so slightly across cosmic scales. Each region becomes an experiment in physics under different conditions of curvature and energy density. The new cosmological humility. Such a view does not discard the old cosmology, it refines it. The universe remains governed by general relativity and quantum mechanics, but those laws may reveal new facets in different environments, like one melody played in many keys. The cosmological principle, once rigid, becomes statistical. The universe is homogeneous on average, but richly varied in detail. Structure is not a perturbation upon perfection, it is the means by which perfection expresses itself. This mosaic interpretation carries a humbling message: we cannot stand outside the pattern to see its full symmetry. Our measurements arise from one tile, our void. What seems anomalous may simply reflect our vantage. Cosmic variance is not failure, it is the texture of reality, a living geometry. Seen this way, the universe becomes a kind of living geometry, regions contracting and expanding, exchanging energy, each influencing the next. Like tectonic plates of space-time, the boundaries between dense and empty zones shift over billions of years, subtly changing the curvature of the whole. Gravity itself may be a dialogue between these regions, a network of mutual adjustment rather than a single, uniform decree. The cosmos is not a static cathedral built once and for all. It is a self-adjusting organism, its laws resonating with the conditions that emerge from them. If this is true, then the constants of nature are not divine numbers fixed at creation, but habits the universe has evolved, stable most of the time, flexible at the edges. The laws are not broken, they are responsive. Each filament, each void, each supercluster adds its own tone to the cosmic chord, and the harmony we call the universe is their collective resonance, the poetry of plurality. To think of the cosmos as a mosaic is to trade simplicity for richness. Uniformity was comforting, variation is truer. It means that the universe's story is not a single equation unfolding in perfect symmetry, but a symphony of local improvisations, matter, and energy composing reality measure by measure. From the outside, if there were an outside, the picture would still appear smooth, but from within each region experiences its own curvature of truth. Perhaps that is why consciousness arose to provide the universe with witnesses inside its own variety. In a cosmos of many tempos, thought itself becomes the local voice of awareness, one tile recognizing its place in the whole. The mosaic is not imperfect, it is expressive. Its unevenness is the grammar of creation. In the next part, the final lullaby of this series, we step back from the science and let the pattern speak for itself, what it means to live inside a universe stitched together by emptiness, bound by gravity, and still learning the shape of its own breath. In the far horizon of time, the universe drifts towards silence. The vast mosaic we've traced, the filaments, clusters, and walls of galaxies will not endure forever. The cosmic web born from density ripples, and bound by gravity's patience, is already unraveling. Its threads stretch thinner with every billion years. The voids, those vast hollows that make up most of space, are expanding faster than the filaments can hold them back. They are not mere gaps, they are the future itself, swelling and merging until they consume almost everything that shines. The great unweaving astronomers can simulate this destiny. Feed the laws of physics into a computer, let the universe evolve forward, and the result is hauntingly consistent. Gravity slows, dark energy wins. Clusters of galaxies, the last islands of matter, tighten under their own attraction, even as the oceans between them widen. The voids surrounding them merge like bubbles in slow motion, coalescing into supervoids hundreds of millions, then billions of light years across. Over trillions of years, these bubbles become so vast that each gravitationally bound cluster drifts alone, cut off from every other by accelerating expansion. Already we see the prelude. The local void around the Milky Way is swelling, its gravitational walls receding as galaxies stream outward. The Laniakea supercluster, our home archipelago of galaxies, will eventually become an island adrift in a black sea. Beyond it, the cosmic web will thin to transparency filaments stretched until they snap their galaxies lost to the darkness of distance. A sky that empties from the vantage of some far future civilization. If any remain, the sky will no longer be the same. Galaxies beyond the local cluster will slip beyond the cosmic event horizon, their light red-shifted until it fades from detectability. Even with the most powerful telescopes imaginable, the universe will appear to end just beyond their borders. Future astronomers born in such a time might believe their galaxy is the whole cosmos, as our ancestors once did. The Hubble flow will no longer be visible. The cosmic microwave background will cool and vanish into wavelengths longer than the size of the observable universe itself. The great cosmic void will have completed its conquest not as destruction, but as expansion beyond comprehension. The slow death of light. On smaller scales, entropy continues its quiet labor. Stars will burn through their hydrogen, then helium, until only faint red embers remain. In 1 trillion years, the last ordinary stars will wink out. Brown dwarfs will fade to black. Planets will freeze their atmospheres crystallized. Only the gravitational whispers of black holes and degenerate remnants will persist, orbiting through the emptiness like forgotten memories. Black holes themselves will not be eternal. Over unimaginable spans, 10 to 100 or 100 years, they will evaporate through Hawking radiation, releasing their mass as photons and neutrinos until nothing of them remains. The universe will then enter its final era, the dark energy epoch, a vast, featureless expansion governed entirely by the cosmological constant or whatever dynamic field replaces it. The web will dissolve, leaving no clusters, no filaments, no maps, just isolated atoms and cold light receding into an unreachable infinity. The echo of structure, and yet the pattern of the web, the fingerprint of those early quantum ripples, will never truly vanish. Its imprint remains encoded in the distribution of what little matter survives in the gravitational waves stretched beyond all scale, and perhaps in the background entropy of the vacuum itself. Even when no observer remains, the shape of everything that once was will still define the geometry of space. The voids will merge into one enormous uniform expansion, a cosmos of near-perfect smoothness, ironically returning to the same simplicity from which it began. It is a poetic symmetry. The universe started almost smooth, grew intricate through gravity's competition, and will end smooth again as expansion erases contrast. The journey from uniformity to complexity to stillness is the story of cosmic breathing, a single cycle stretched across eternity. The human scale of infinity. What does this fate mean for us creatures of one brief filament within the web? Perhaps that transience is the price of structure. The very emptiness that ensures our existence will someday reclaim it. But there is comfort in that inevitability. Every star that burns, every atom that vibrates, is a momentary resistance against perfect equilibrium, a flare of order in a universe that longs for rest. Physicists call that final rest, heat death, a state of maximum entropy, where no work can be done, no gradients remain, and time itself loses meaning. Philosophers might call it silence, yet in that silence lies fulfillment. The universe, having explored every possibility, settles into completion. The great void becomes not a failure of creation, but its last and most complete expression. The poetry of the end. Imagine it then, 1 trillion years from now. The last photons drift through infinite darkness, their wavelengths longer than galaxies once were. The curvature of space has stretched nearly flat. The cosmic microwave background, our oldest light, has been diluted to 1 ghostly photon per cubic kilometre. No life watches it fade, but the geometry remains a fossil of what once pulsed with stars and thought. And somewhere in that endless quiet, the physics we've uncovered, our equations, our telescopes, our questions are folded into the fabric itself. They were the universe learning to understand itself before falling asleep again. The void that surrounds us now is a glimpse of that destiny, not nothingness, but completion. The final architecture of existence is emptiness perfected. When future expansion makes every atom its own isolated world, the universe will end as it began, not with fire, but with breath. One last slow exhalation into eternity. You lie beneath a sky that has been expanding for 14 billion years. Every second, the light that touches your eyes has travelled through growing emptiness, through the quiet corridors of the KBC void, across filaments of galaxies thinning like silk threads. You're inside a bubble, not metaphorically, but literally a hollow of lower density, a pocket in the cosmic foam, where gravity's pull has loosened and space breathes a little easier. And yet in that breathing space, life arose. Against the faint hum of the cosmic microwave background, atoms assembled into oceans, forests and consciousness. Somehow in this thin oasis between clusters of galaxies, a species learned to build instruments, name the stars and ask where everything began. the center that isn't. There is no true center of the universe, no privileged location, no favored coordinate. Every observer anywhere sees galaxies receding equally in all directions. Expansion is not motion through space, but the growth of space itself. Still from within our void, we experience something like a center, a calm region surrounded by distant brightness. It feels local, personal, meaningful, because it is the place from which we look out. The quiet center is not in the sky, it is in the act of seeing. We are each of us a temporary witness stationed within one cell of the cosmic web. The laws we measure here are Hubble constant. Our cosmic time are local notes in a greater symphony. Far away, other voids and clusters beat to slightly different tempos. Together they compose the living rhythm of the cosmos. And through that rhythm runs a single thread, the human ability to feel awe, the humility of smallness. To grasp the scale of what surrounds us is to feel a kind of peace. Our entire history, the rise of civilizations, the music of thought has unfolded in one corner of one galaxy, inside a bubble only slightly emptier than average. Yet from here we have mapped the shape of all things. We have watched galaxies drift apart, weighed the invisible matter that binds them, and traced the whisper of the first light. The void that might have erased us instead granted us perspective. When you look up tonight, remember you are seeing only the tiniest fraction of the whole, and that is enough. The starlight that reaches you has crossed billions of years to die softly in your eyes. It is a conversation between what endures and what vanishes, a dialogue the universe keeps having with itself. Gratitude in the hollow. Perhaps that is the hidden purpose of emptiness, to make room for reflection. In the spaces between stars and thoughts, between one heartbeat and the next, the same silence resides. It is not absence, it is invitation. The cosmos leaves room for gratitude. To live inside a void is to be given space to wonder. To rest in it is to belong. The lullaby of expansion. Even now the universe is stretching. Galaxies recede a little faster. Light reddens a little more. The fabric of space hums with faint acceleration. But expansion is not escape. It is the universe breathing out, creating distance, so that complexity and calm can coexist. In time, everything will drift beyond visibility, but the pattern will remain the memory of connection carried forward in geometry itself. And here on this small planet, spinning in the dark, you can close your eyes and feel that same rhythm, the slow, endless pulse of creation still unfolding. It has no boundary, no edge, no hurry, just a quiet continuity that has outlived galaxies and will outlive us all. The quiet center of everything, so rest now. The equations have done their work, the telescopes have gathered their light, and the story of the void has been told. Somewhere beyond our reach, Euclid's mirrors and Roman's lenses are still watching the faint shapes of galaxies bend through space-time, measuring the breadth of the universe as it exhales. But here inside your own small gravity, well, you can let the numbers fade. The universe will continue expanding whether you watch it or not. It will carry your atoms outward someday into the general circulation of stars and dust. And in that distant future, when even starlight has gone, the trace of this moment of a mind quietly aware of its place will still be written into the fabric of what was. The cosmos is vast and we are brief, but the wonder fits perfectly between the two. You're inside a moving bubble floating in an endless sea. And for now, for this night, everything is still, everything is enough, everything is at rest. Good night.